Perfect.
Yeah.
Go ahead.
Shall I go ahead?
Yeah.
Good afternoon, dear participants. Warm welcome to all of you. And we wholeheartedly, on behalf of Vishwesvaraya Technological University, we also welcome Dr. Pallavi Goswami from Australia. Thank you, madam, for joining us. Let me briefly introduce her. Dr. Pallavi Goswami is a postdoc research fellow in the School of Earth, Atmosphere and Environment at Monash University, Australia. Her research focuses on understanding droughts. It might be related to meteorological, hydrological, and agricultural. Their onset time frames, it might be flash or versus slow. Process characteristics, drivers, and their compounding, cascading with other hazards such as floods or floods to drought transaction, etc. Her present research is part of the Climate System Hub of the National Environmental Science Program, NESP, funded by Australian government. Dr. Goswami did a joint PhD with Monash University, Australia and IIT Bombay, India in hydrology and her interests include extreme events, non-stationarity of weather hazards, and hydroclimate changes and variability. She is also interested in understanding future projection of extreme events, including implication for adaptation. So with this brief background, I welcome you, Dr. Pallavi Goswami, and I request you to please continue your session. Thank you, madam.
Yes, thank you. Thank you so much, Professor Chandrasekhar. Really thankful for this opportunity to be able to speak today in this 6-day online faculty development program. Yeah, thanks for the introduction. I am Dr. Pallavi Goswami. I'm a postdoctoral researcher at the School of Earth, Atmosphere and Environment at Monash University in Australia. I'm joining from Australia at the moment. And so today I hope to present some of the research that I've been doing to sort of fit into this context of energy sustainability and climate change. So the topic that I am going to be talking about today is climate-informed water resources management in the face of global change. I know Professor Chandrasekhar gave an introduction to what I do, but I just thought I'll briefly discuss what's my background, where I'm coming from, and the kind of research that me and my colleagues are doing here in Australia. So I did my PhD in hydrology and water resources engineering. Prior to that, I finished Bachelor's of Technology in Civil Engineering. And in my research, my main areas of interest are looking at hydrological extreme events such as droughts, floods, heat waves, bushfires. I try to understand how water availability might be changing because of changes in climate or changes in climate variability. So I try to understand these through using statistical models and a concept that's called non-stationarity, which I'll be discussing in my slides ahead. But yeah, just to give an overview of what I do. So I try to use data, try to understand how hydroclimatic events might be changing and how we can get a better handle on these. So a large part of my work has been centered around understanding droughts. How do they onset? What are the time scales? What are the different types of droughts? Like we've got meteorological droughts, agricultural droughts, hydrological droughts. I know we've got a mixed bunch of audience here, so I might be using some jargons, but I'll try my best to dumb it down to explain what exactly I'll be talking in my slides. So my work mainly deals with understanding how droughts might be changing with changes in climate. And so I try to understand climate and the different drivers of climates and how they might be affecting the precipitation that we receive, the soil moisture, which governs the agricultural outputs, and the flows in our streams and rivers, which then govern how much water is available to us in reservoirs or in rivers. So, like I said, I work a lot on understanding hydroclimatic extreme events, and these are just a few of the snapshots of some of the recent hydroclimatic extreme events that we've been having. On the top left is the recent cloudburst, as you would all know, that took place in Uttarakhand in this year. Below that, I've got a picture of the floods that took place in Kerala in 2018 that led to massive inundation. In the middle, I've got a picture of drought, which took place in 2015 in the Marathwada region of Maharashtra. The picture shows how, what was the scarcity of water at that time and how people were really fighting to get some water for themselves, for their utilities and for their fields. We've also have something called the bushfires or wildfires events, where extreme heat can also lead to burning of forest. So this picture that you see is from a very famous incident that happened in Eastern Australia in 2019. So end of 2019, during the summers here in Australia, we had a massive bushfire event, which was following a major big pre-year drought period. And then another extreme hydroclimatic event that we study is heat wave, which is getting more common, especially in North India. So this is a snippet of the heat wave that took place in Delhi in 2022. And just to say that it was not just Delhi, but then many other regions in India were impacted in 2022 because of that massive heat wave. So these hydroclimatic events are changing. We're seeing them more often. And what we know from past literature is that climate is definitely an important factor that controls these extreme events. However, climate is not the only factor. There are other factors such as land use change, so how the land is being used. Let's say if we have more urbanization, that can change, let's say, the extreme rainfall events that we see in a particular region. Then population is another factor. Population controls the vulnerability of any region to these extreme events. And so the impacts are directly linked to population. So if you've got more population, you've got a higher exposure. And so that can lead to the increased risk that we see from the impacts of these events. And also, which is important, and I would like to highlight that, is the policy and the governance. So the way the rules work to, set the availability of water and how the water is distributed, how much, let's say, water is released from a reservoir and all those conditions, and how the climate preconditions play a role in the decisions that are taken are very important in deciding how much a particular hydroclimatic extreme event would have an impact. But for the greater part of my talk, I will mostly be focusing on the influence of climate and how changes in climate is impacting water availability and water as a resource. And when we talk about climate, we know that climate has an important role in the hydrological cycle, as we know. So hydrological cycle basically is the water cycle around the Earth. So we've got water evaporating from the ocean and the water sources that we have on the land. And then the evaporated water goes up, forms clouds, and then precipitates again in the form of rainfall or snowfall, and then joins the streams. And so that completes the hydrological cycle. So climate and meteorological variables or climate drivers are very important for maintaining this hydrological cycle. And so any changes in the climate would impact the hydrological cycle. It could make it more intense, or it could make hydrological cycle more severe, causing more damage. So when we have this link between the climate and the hydrological cycle, what we also know is that hydrological cycle can lead to extreme events in some cases, such as droughts, floods, and the other events that I listed in the previous slide. So there can be a possibility that it might increase the frequency of these events. And also when we have these extreme events and climate that might also lead to water quality issues and water availability issues in general. So this presentation would have a lot of figures, as you would see, taken from the IPCC report. So IPCC, the Intergovernmental Panel for Climate Change, has been doing pioneering work to ensure that we are fully aware of how the climate has been changing, what's the science behind it, how we can work towards the adaptation, resilience, how we can understand what's our current vulnerability, what are the current impacts of the climate, and how that would change in case if we do not curb our emissions, or if we modulate the socioeconomic policies that we have in place. So the IPCC has done a fantastic job in coming up with its assessment reports, and the recent one was back in the year 2021 and 2022, which is called the Assessment Report 6. And so that briefs us about how briefs us about almost everything that we know of the climate historically, based on observations and model analysis, as well as what the climate could look into the future. Let's say if we continue business as usual, if we continue the emissions the way we're doing it at the moment, or if we do have some hold on the way these emissions are being put out in the atmosphere. So this is a fantastic report, and I would really encourage you all to go through the summaries so as to get a glimpse of where we stand in terms of how the climate is impacting water availability. And all this is highly linked to the sustainability development goals, which were established by the United Nations, particularly the one on climate action, sustainable cities and communities, clean water and sanitation, life on land, and life below water. So this is not any new figure that I'm showing here. I'm sure most of you would know that we're having convincing proof at the moment that the global temperatures are increasing. So the figure on the left is basically the temperature anomalies over the years, starting from 1950 up to the present time. And as you can see, we are continuously on the rise. So there's a significant increasing trend in the temperature, and the planet is significantly warming with time. And this has been attributed to the carbon dioxide concentration that we have in the atmosphere. As you can see, the trend in temperature is analogous to the carbon dioxide concentration that we see here in the plot on the right. So carbon dioxide basically has a really high radiative forcing, which means that it has this greenhouse effect. So incoming solar radiation gets trapped because of the greenhouse property of carbon dioxide, which is what leads to an increase in the temperature that we feel. Although I would like to say that carbon dioxide is not only, it's not the only gas that's responsible for the greenhouse gas effect that we see in the global warming. There are other gases that we have in our atmosphere which are also leading to increase in temperature that we see. But carbon dioxide by and large is the biggest culprit that we know as of now. And the emissions that we've been putting out in the atmosphere is one of the most important factors that's causing this global warming. And so how does that global warming sit in the picture of water availability? As I pointed out in my previous slide, climate governs water availability through the hydrological cycle. So the figure on the left is basically the hydrological cycle, which I described a few minutes ago. We've got precipitation, precipitation in the form of rain or snow that comes down from the sky. We've got, so the precipitation feeds into the surface runoff. We've got streams. We've got surface water bodies such as lakes. And then all these drain into the ocean, the seas, from where they evaporate. They also evaporate from the land. So basically all the evaporation that happens, as well as the transpiration, that's the loss of water from the plants, all again goes up, it condenses to form the the precipitation. So this is a very idealistic as well as a very simplified way to look at the water cycle. However, what I don't show in this figure are the drivers of climate, or the meteorological drivers that actually govern each step of this water cycle, which is what is shown in the figure on the right. So we've got multiple factors here. We've got radiation, we've got temperature, we've got wind, humidity, and all these things influence these processes that are part of the water cycle. And these climate factors then determine the water availability that we have in our streams, rivers, the groundwater that gets stored, or the water that's stored in the lakes, the reservoirs, as well as the water that's stored in the soil in the form of soil moisture. So if we talk about streams, let's say if our streams do not get the sufficient water that they need, then we would have something called a hydrological drought. So hydrological drought is basically when we do not have enough surface runoff. And also for groundwater and lakes and reservoirs. So all the surface storages of water, if they are anomalously dry, and by anomalously dry, I mean when they are dry with respect to their climatology, or what's expected of them to be normal levels of, let's say, stream flows or groundwater levels, then we are in a hydrological drought. If we do not get enough precipitation, if we do not get enough rainfall, then it leads to something that's called a meteorological drought. So basically, in simple words, it's just deficiency of precipitation. If we expect monsoon to, produce X mm of rainfall during the June, July, August, September season, and if we don't get that much of rainfall as expected, then we are in a meteorological drought. Monsoon could be considered to have failed for that year. So that's basically got to do with precipitation. There's another type of drought that's called agricultural or ecological drought. That's to do with soil moisture. So if our soils do not have sufficient water, it can lead to wilting of plants, which means that plants cannot extract water that's there in the soil, and hence it would lead to vegetation dieback. It'll lead to crop failures, and hence give rise to something that's called an agricultural drought. And drought, irrespective of what nature it is, it has environmental impact because all these systems are heavily intertwined. It's a very complex system. If one aspect or one component of the system is in deficiency, it generally has a cascading effect. What I mean by cascading effect is that most of the time drought starts as a meteorological drought. So we don't have sufficient rainfall, but that sufficient rainfall does not produce, let's say, sufficient stream flows. And so it causes a hydrological drought. And because there's not enough rainfall, there's not enough water in our streams and rivers or in the ground, so our soils do not have the water that they need for a healthy crop or for the trees and the forest. That's why we then see an emergence of an agricultural drought. So usually drought often cascades down the hydrological cycle, and so it inevitably impacts the environment and the socioeconomic sectors that are dependent on it. So, so the IPCC report, the assessment report 6 that came out in 2021, had a detailed analysis of how the different components of the water cycle have been changing based on what we know as of now. So the four most essential components of the water cycle are the precipitation, the runoff, or basically the water that flows on the surface to join the streams, evapotranspiration, which is both evaporation plus transpiration, and then surface soil moisture. So these 4 quantities are by far the most important components of a water cycle. And we, as climate scientists, are extremely interested to see how these have been changing over time. Is there a trend to it? Are we getting more dry in some region? Are we getting more wet in some regions? So this is basically a figure from the IPCC report where they have analyzed something called the something called SSP, the Shared Socioeconomic Pathway. This SSP 4.5 is basically a moderate scenario. So it expects that the future, we would still continue to emit carbon dioxide, but those emissions are moderately high, but not extremely high. So it's not the best scenario that you would want. It's also not the worst scenario, but it's sort of a moderate scenario. So this figure is basically showing how would the precipitation, evapotranspiration, and all these things would look like in the future. And the future is 2081 up till end of the century. So the last almost 20 years of the century, how would that compare to what we know from, let's say, the data 1995 to 2014? So let's say if we look at precipitation shows an increase over the Indian region. As you can see, the green color highlights percentage increase. So some regions of the world are expected to get more wetter, and there are also regions which you would see are in brown, like this part, southwest of Australia, some parts of North Africa, and also North South America, especially in the Amazon River Basin. So those parts are basically expected to receive less rainfall in the future if we continue our emissions based on the radiative forcing of 4.5. So it is a mixed picture, but what it means is that some regions would be getting more rainfall and some regions would be receiving less of rainfall. So regions where you would expect rainfall to increase can have an increased likelihood of experiencing floods. And regions where we see a drying trend are regions where we can expect droughts to be more intense, more longer, probably more frequent as well. But yes, so that's how you basically interpret how a region would probably be impacted by changes in global warming. And this figure also has information about evapotranspiration, runoff, and surface soil moisture, just to give you an idea of how the different water components might be changing. Runoff generally means you would expect a surplus of water compared to the climatology, so more water than what we normally get at the moment by the green color, and then the brown color is where you would expect less runoff, so less volume of stream flows, less volume of groundwater storage, less volume of water in the lakes, reservoirs, etc. And surface soil moisture is again important because India, for example, is primarily an agricultural-driven economy, and so are many other parts of the world as well. So we want to know how much water would, in general, be available in the soil. Are we going to see more of agricultural droughts? Is the soil going to lose more moisture as we proceed because of the global warming? So not a very great picture with respect to soil moisture. As per IPCC, we have a lot of drying, as you can see, a lot of regions in the brown color, which means less and less availability of soil moisture and hence less water available for crops and for plants. This is another image that is with regards to the recent trends that we have from the GRACE satellite data. Understanding how much are we doing in terms of the global water storage capacity at any given point in space. So the regions in red are basically where we are having a decline trend in the stored water, and the regions which are in blue are basically regions where we are having an increasing trend, so more like surplus of water stored. Again, as you can see in India, we've got a mixed picture. The north part is not doing pretty good. We've got a declining trend. Groundwater depletion has been taking place in the north. But then there are regions in the south where you can see this blue color. So there is an increase in the surface water storage, which probably could be because of an increase in the precipitation that we've been seeing over the years. Because I do a lot of research in Australia, I'm particularly interested in how the water availability in Australia is changing. So the north part of Australia also receives water from its own different monsoon. It's different from the monsoon that we have here in India. But then the north part of Australia is going to get more wet seasons. And so at the moment, we're seeing a more increasing trend in the water in general. But then the south as well as the west part of Australia has been seeing a decline in the global water storage. This is as per the GRACE satellite data. There are some uncertainties associated with these data, but then they are a good enough picture to see how we are faring in terms of the water storage at any particular point of time. So I'm trying to present more and more evidence to convince you that global warming is having an impact on the water cycle. And this figure also is something that's adding information to show that there is an increase in the percentage of the changes in the water cycle with respect to every degree of warming. So I don't want to go into the nitty-gritties of it because then it might get complicated, but just to keep things simple, what we have on the x-axis is basically every degree of warming, every degree of global warming. And then on the y-axis, we've got the percentage changes that we see in the land water cycle. As you can see, we've got this increasing slope. So every time we have global warming increase by a certain percentage, there is an impact on the water cycle. And because my particular research is a lot centered around droughts, so I particularly am very interested in understanding how droughts have been changing, how droughts, especially the drought risk, has been changing. So this slide over here is giving a picture of how the global drought risk has been for the entire Earth. So risk basically is derived using three different components. It's a function of hazard, vulnerability, and exposure. So all these components of risk work in conjunction for us to understand how the risk of a particular extreme event, drought in this case, is changing. So as you can see, the top figure here is about drought hazard. So this has got to do with how the climate is behaving. Hazard is directly linked to the climate. However, when you talk about vulnerability and exposure, they are independent of climate. They depend more on the socioeconomic conditions. So vulnerability of a region to drought would depend on how equipped, let's say, the region is to experience a drought. How much are they, having some, let's say, alternate means to supply water in case if the rainfall fails, or how much money do they have to put in, some infrastructure that can actually nullify the impact of, let's say, a failed monsoon. So vulnerability is purely a socioeconomic aspect. It's got nothing to do with climate, but remember that does inflate the risk that we see overall. So the vulnerability map is shown in the figure on the top right. Then we've got exposure. Exposure mostly is governed by population. And as you would expect, India being the most populated country, we have a very high value of exposure. And this holds for other extreme events and not just droughts. So in general, India has higher exposure to any hydroclimatic extremes that we talk about. And so it makes it even more important for us to take measures to control the risk of these hydroclimatic events. So risk basically, in simple definition, is a product of the hazard, the vulnerability, and exposure. The talk that I'm giving today is dealing more with the climate part, which is the hazard part. But nevertheless, I would like to flag that the overall risk of any hydroclimatic event is also factored in considering vulnerability and exposure. So the future, so that was basically how the droughts have been globally. So this was the current picture of how we know about drought risk, and apologies, I forgot to mention that the drought risk is pretty high for India. But this picture is what we know of the current drought. So that's our current understanding of droughts. This is one of the studies that was done to understand how the future drought risk might look like. And what this study also does is it also goes back in time as much as is possible. And as many of you would guess that we did not have observations back then. So a common practice in hydrology is to look at tree rings. So tree ring data is basically proxy of what might have been the condition back in the time when the tree was at a particular stage of development. So with the information that's stored in tree rings, we can do something called a paleo analysis, so paleoclimatic analysis of drought. What I have here on the figure, what I have here in this figure on the left is basically an example of how one of the drought indices has been evolving over time. This is for different regions of the world. So this study looked into Mediterranean, Central Chile, Western North America, Eastern Australia, New Zealand, and Central Asia. And what I have on the y-axis is one indicator of drought. It's a very popular indicator, which is called PDSI, so the Palmer Drought Severity Index. It basically tells how much severe the drought is at any given point of time. And so this gives you a holistic picture of how drought in a particular region has been evolving over time. And interestingly, the right side of this is the recent years. And what we do find is that we see this dip in PDSI. And the dip is basically indicating an increase in drought. So PDSI, which is the indicator for drought, if it's negative, it's indicative of drought. And if it's positive, it's opposite. So it's more wet, more water available, right? So what we see in this particular image is that in the recent years, a lot of the regions have seen a sharp decline in the PDSI value, which means we're having more severe droughts compared to what we had, even including the paleo records and not just the observational records, which is not a great news, which means that these regions are getting worse and worse with respect to droughts, and hence less water availability. So the figure on the right is basically another figure that I took from the IPCC report, where they've highlighted the regions where droughts are expected to increase in future. So Southwestern Australia, where I also particularly do some of my research, is expected to experience more drought. And then, yes, some other parts of the world, including the big Amazon basin. So regions where there is a lot of water in general available, people where wouldn't expect droughts to happen, are going to experience severe and more increased droughts in future. So now I would like to introduce the concept of non-stationarity. And this is very important because we are seeing a change in the climate. And so the concept of non-stationarity, I know it sounds like a very, it sounds like something that is probably like, gives you like a scary feeling of what that really means, because it's got to do a lot with statistics. But what we generally do in terms of like designing water systems is by looking at the distribution of rainfall, distribution of something called, the IDF curves, the intensity, duration, frequency curves. So these are all the design curves which go into designing any water infrastructure. But what I would like to highlight here is that a lot of the infrastructure that we have are based on stationary distribution. So what is a stationary distribution? You would have all heard of probability distribution. So probability distribution is basically, you've got a data and you try to fit a probability distribution by estimating the parameters of a distribution. And generally, what we assume is that those parameters of the distribution are constant. They're not changing with time. But recent studies have shown that the distributions have been changing with time. And so what this means is that if a distribution is changing with time, the parameters of the distribution might be a function of something with respect to time that's causing the distribution to shift. And why is this the case? Because we are not able to explain all the data that we're seeing, especially with respect to the extreme events, if we fit using stationary distributions. So we cannot explain all the extreme and the outlier and the tail behavior using simply a stationary distribution, using simply one distribution with constant parameters. So a bunch of scientists came together to prove that there is non-stationarity, and hence we need to increasingly factor in the changing aspects of this distribution if we really are to design water infrastructure that can survive, let's say, the future extreme flood event or extreme cloudburst or glacial lake outburst events. So just listing a few studies here that also were quite seminal papers in themselves, highlighting the fact that the engineering designs that we have, they need to be updated. We need to update the IDF curves. We need to update the design curves and need to factor non-stationarity in. One example of this non-stationarity was during the Millennium Drought that took place in Australia. So the Millennium Drought is pretty well known. It was a 13-year-long drought that took place, particularly in the southeast part of Australia. And what hydrologists found over there was that the rainfall runoff relationships were very different. So what ideally you would expect a given amount of precipitation to result in a form in the stream flow, that was not the same. So the same amount of precipitation was giving less surface runoff, which means that the data somehow was coming from a different distribution, or basically the relationships between the rainfall and runoff had changed. This again is an example of non-stationarity, and a single distribution cannot explain it. So what we did in our research, and I'll not again get into the nitty-gritties of it, but just to give a perspective and a flavor of what we were trying to do, was we were trying to see if the stream flows that we see during droughts, are they impacted by large-scale climate drivers in a non-stationary fashion? And so by doing this, we can answer questions like large-scale climate drivers such as the El Nino, which is the most popular, one of the most popular modes of climate variability. I'm sure a lot of you would have heard of El Nino. And there's also something called the Indian Ocean Dipole moment. So these are basically natural modes of climate variability. These are part of the natural climate of Earth as we know. They are different from climate change. So climate change is basically global warming that's happening, that's increasing the temperature. But El Nino, Indian Ocean Dipole, these modes of climate variability are part of the natural cycle of the Earth. They take place at a frequency of once in 3 or 4 years. And so they can cause more rainfall, or they can cause less rainfall. So they can cause floods or they can cause droughts, depending on their phases. So what I was trying to do here in my research was, given that we had this information that the rainfall runoff relationship was exhibiting non-stationarity, do we also have non-stationarity with respect to climate? And what this would result in is establishing that climate is very central to water availability, but using a non-stationary framework. So the advantage of that is you can also factor in changes in these natural modes of climate variability. Like I said, I wouldn't get into the statistics of the model, but we basically modeled the intensity, duration, and frequency of the hydrological droughts that we were experiencing in Southeast Australia. And we were trying to see if a non-stationary model could explain that. And we found that, yes, a non-stationary model was better able to explain the changes in the water availability that we were seeing. So this is just a picture of how the intensity was looking different for the 3 different climate drivers that we looked into. So you can see that there is a slight shift in the two probability distributions, which means that you cannot use just one distribution and explain all the data that you see. So basically trying to understand the intensity of the hydrological droughts, the duration, again, you can see that the distribution is sort of shifting towards the right. So which means like when you've got a dry phase of ENSO, you can expect longer duration of these droughts. Similar results for annual frequency. Again, when you have a dry phase of ENSO, you can see it's got a higher probability of positive frequencies. So basically, in a nutshell, what this study was able to show was that there is influence of these climate modes on the stream flows, and that influence is non-stationary. It would depend on how these climate drivers are changing. So, so with this non-stationary framework, there are a couple of things that we can do. We can try to understand how the dry phase of, let's say, the El Niño Southern Oscillation would shift the low flow characteristics, or the wet phase, how that could sort of shift the low flow characteristics again in some other direction. So in a way, changing the probabilities of what we expect of a given low flow characteristic. And with this framework, what you can also do is you can see how this information would translate into the future. So let's say if you know how a future El Nino would behave, you could predict how your drought characteristics would look like. And also because I mentioned that El Nino, for example, is part of the natural climate variability. However, global warming is having an influence on these El Nino events. So what this means is that even though there is a natural climate feedback cycle of the Earth, but the global warming has a feedback loop that then controls these events. So what this means is that these events, which are supposed to be behaving in a more natural fashion, also have the potential to get intensified because of global warming. So there's a chance that we can see more intensified El Nino and hence more intensified droughts, for example. So just a example of how this has been changing. So the figure on the right is basically how the El Nino has been changing over time. As you can see, the magnitude has increased. So we are seeing like the swings from El Nino to La Nina, from the dry phase to the wet phase, get more intensified. So more intense droughts, more intense floods. So with that information, like I said, what we can also do is project those intensities, duration, and frequency of droughts and see how those will be shifting. Again, I'm not getting into the details of this. We can discuss this if somebody has a specific question on this, but just to give you a flavor of how the intensity, duration, and frequency are shifting when we've got this projected data. So projected data is basically the orange curve, and the yellow curve is basically what we know as of now of their present phase. So the projected part is again shifted towards the right, which means the tail is getting heavier. So more probability of intense, longer, and frequent hydrological droughts. What we also know as non-stationarity is this probability distribution changing, as I said. What this could mean is that droughts itself would start looking very different, right? So what we wanted to also look at in terms of understanding droughts is that are droughts having a shift in their states? So what does that mean? In simple words, imagine a system which has a particular value that you would expect. It might fluctuate along its average value, but then again, it's sort of, it's within a predictable band. But then imagine some forcing, some climate forcing that causes this system to tip over and start behaving in a very different fashion. And so it goes in a different regime. And this new regime would again have values, but the mean would be very different. So what this means is that sometimes hydrological systems can have multiple states. Say, for example, if you're talking about droughts, because that's what I've been talking in my previous slides, droughts can also have two states in the sense that they can have two regimes. So maybe what is an intense drought today might be a normal drought maybe 30 or 40 years into the future. And what we might not be observing now as intensities of, let's say, precipitation deficits could also be something that we might start observing in some point in future. So what I'm trying to say is there is a potential in the climate forcings to disrupt the way our hydrological extremes look like. We might start experiencing extremely severe values of climate variables, or for example, stream flows or rainfall, which we've not seen in the past. And so that's what we call a regime shift. So in this work, and I'm not going into details of this work, but in this work, we showed that there is a possibility that some hydrological disturbance, which could be governed by some climate trigger, can lead to these kind of regime shifts. And then this is, again, a whole different research problem in itself, because then we have to answer question as to what's causing these changes. But at the moment, it's good to just know that there is evidence that you can have really different states of droughts. Droughts can start looking very intense, or they might actually look less intense. For example, for regions where you're going to have more rainfall in the future. So what is a severe drought today might not be severe in the future, and vice versa. So this is just one example of how we were trying to look at changes in the states. So this is basically the intensity of the drought. And this is taken from a catchment which experienced drought during the Millennium Drought, which was a severe 13-year-long drought that I spoke of a few minutes ago. And what I show over here is that in the green color was the intensity of drought over these years. But when this Millennium Drought happened, the catchments started responding in a very different way. And we started seeing more intense value of droughts than what we were seeing previously, which means that meteorological drought that took place in this 13-year-long period actually intensified the stream flow droughts that we were observing on the ground. So again, example of non-stationarity. Now I'll be talking about something that are called flash droughts. So this is again part of the different hydroclimatic events that we're experiencing. And flash droughts are basically droughts that happen really quickly. So they have a very rapid rate of onset. And why are they sort of getting more attention these days is because droughts are supposed to be a creeping phenomena. They're supposed to be having a very slow onset. They take a lot of time to, really show on the surface. Plants, dying or the crops failing. That's basically like really a large time scale matter of fact. But what flash droughts are basically droughts that happen very rapidly. And so how rapid is rapid? I'm talking about time scales of days and weeks. So yes, there is a possibility that droughts can onset in just a few days, as opposed to the conventional belief or the traditional belief that droughts take months to happen. This happens when you've got an increased evaporative demand. So they basically, the increased evaporative demand sucks out the water that's there in the soil, leaving the soil depleted in moisture, and hence leads to the wilting of vegetation. And as you would expect, as you would expect for any drought, these flash droughts also impact agriculture, livestock, economy, and all the important sectors that are dependent on them. Yes, so we were trying to understand how rapidly can drought onset, and understanding this is important because again from the perspective of water management, we need to know how quickly can we lose our water so that we design the infrastructures, or we design or plan the water resources in a way that we factor in the time in which we can really lose the moisture that's there in the soil, or lose the water that's there in our the water bodies on the surface. And so what we show in this study, again, this was based in Australia, but these results are applicable to other parts of the world as well. What we show in the study is that most of the regions in Australia, for example, can go into droughts in just 10 to 15 days when you talk about flash droughts. which is a considerably short period of time. Imagine a really large area suddenly going into drought. And what if there are not, some policies or other alternatives of water available? And if this happens, especially in the middle of, let's say, the important growing season or the important water, the watering season of the crops, then it's going to be a huge loss for the farmers, right? And so this is what is also more important when we're talking about flash droughts, because we need to know the whole spectrum of the distribution of the onset days. We really need to get a better handle on understanding how quickly can we lose the water that we already have on the ground. Let's say in case if there are really high temperatures or really high evaporation happening. So because global warming would also lead to like more increased temperatures, also would lead to higher evaporation rates happening, then we really need to be prepared for situations where drought will onset faster compared to the conventional droughts. And we need to have resources, we need to have water backups in case if that happens at a critical part of the year. And that's not just all. We also have compounding and cascading events. So we've got increasing evidence of droughts and floods happening back to back, which is like two, big impactful events. When they happen back to back, that you can imagine that's going to increase the amount of economic damage that the societies undergo, as well as the impacts, because it's not now just one extreme event, but it's multiple extreme events happening one after the other. The other example of compounding events could be when we have a heat wave within a drought, which again is quite likely because usually droughts would have periods of extreme high temperatures, low humidity, and all these factors are also the factors that cause heat waves. And so what is also potentially going to be more likely in a future that's more warmed up is a cascading and compounding element of these hydroclimatic events. So there will be more chances of droughts compounding with heat waves, or for example, droughts compounding with bushfires or wildfires. So the example that I presented in one of my earlier slides, the bushfire event of 2019 in Australia, was following a 3-year-long severe drought period. And that was a really good example where we saw compounding of hazards, so droughts, which led to bushfires. And the other thing that I mentioned was we can also have something called droughts following floods. So that's a new kind of hydroclimatic cascading events that we're seeing, which is pretty counterintuitive because you would not expect floods to follow immediately droughts, but that's happening. And I've got one example here at the bottom, which is from one of the states in Australia. This example basically shows that in the month of September to in the month of July to September, we had pretty dry conditions. Some regions were extremely lowest in terms of the rainfall. Some regions were severely in deficits of rainfall. But then this picture that you see is in the month of October, so the 4th of October, we had the same region that was experiencing severe deficiencies for the last 3 months had an extreme rainfall event. And so what this can actually do is this can compound to the miseries for the people. People might not be expecting a flood event. And so the infrastructure or, basically the kind of management that would be ongoing for catering the drought would not be able to cater for the flood because that's very counterintuitive. However, we have been finding increasing evidence of these events where we've got droughts followed by floods. And so this again just adds to the complexity of this whole picture of how climate can play, really nasty games with the hydrological cycle and can lead to all possible, combinations of different weather events happening together. And then, there can either be like, floods or droughts or heat waves and all these things which were pretty less common in the historic records. I would wrap up here, but yes, before I conclude, just sort of to give some take-home message from what I've been discussing in the slide so far. So yes, climate-informed water resources management is important because we have evidence that there is non-stationarity. The things are changing with time, climate is changing, and that changes the way the hydrological cycle behaves and the extreme events that we've seen. And so there's a need to manage the water resources in a way that meets the changes in the climate. Climate change basically is a big challenge, and we should not have assumptions which sort of makes us feel that, oh, climate is always varying and it's going to always go up and down. It's not going to really lead to an overall intensification. Or so I think it's high time we really challenge those kind of assumptions that we've been making, so that we can revise the designs of water infrastructures and the adaptation measures that we really need to put into place. So there's also a need to integrate projection, scenarios, and risk, and the IPCC report really does that beautifully. They've done a good job in telling us what the projections would look like if we continue with the emissions or if we curb them in a certain way. And so it's important to understand how the future of water availability would look like, how the future with respect to climate extremes would look like, and to factor in all the scenarios. Let's say, if we take a different socioeconomic path, how is that going to affect water availability at a given point of time? And so we need to work it backwards and see what decisions we should take today and in the coming future, so that we minimize the risk that's associated with changes in water availability. And all this, again, underpins the importance to build in more resilience and adaptability in the policies and the governance that we're having at the moment. There definitely has been a lot of progress with respect to the global climate models and regional climate models. There's been quite an improvement, and we're now able to be more confident, and we're trying to reduce the uncertainty in the projections as well as in how the simulations of these climate models are working. We need to still keep working to improve the present forecasting system of drought, flood, and other extreme events, so that we are factoring in the changes in the climate and also becoming more confident that the forecast is more likely to result in is not likely to result in something that's called a false alarm. And yes, we've got nature-based solutions as well. As you would know, one example that comes to my mind is an increase in the cyclones that are happening in the Arabian Sea. We're seeing an increase in the number of cyclones that are hitting the west coast of India. So what people are actually doing over there is they're trying to have more mangroves planted there, because mangroves can serve as natural barriers to the gust that comes along when there's a cyclone. And so that's an example of nature-based solution where you use nature instead of artificial or man-made infrastructure to sort of deal with these extreme events. So yeah, nature-based solutions is definitely a big plus when it comes to working out the adaptations and solutions to these problems. We need to have a decision support system that is working more actively, so that it minimizes the impacts and the repercussions from these hydroclimatic events. With respect to water, because I've been talking so much about water, there needs to be an integrated water management approach. This is not a new concept, it's an age-long concept, but we need to make sure that whatever integrated approaches we are using or have been using are sort of matching how the climate, what the climate demands at the moment. And yes, of course, pushing for policies that work in the direction of adaptation and resilience. Yes, we need to also work for early warning systems. So the event that happened, let's say the cloudburst event that happened in Uttarakhand, could that have been prevented? Was there enough early warnings for that event that we saw? Was there enough forecastings that could have prevented that, the damage that event caused? So all these questions are still, quite sort of open at the moment. And myself as a hydrologist, we often, really want to sort of get more closer to have, as much information as possible, so that we are able to feed the right information into these early warning systems, so that we can minimize the damage that we see. And yes,
Pallavi,
yeah.
Your slide is being freezed. It is in 20-second slide only.
20-second slide?
Yeah, it is still in the 20-second slide only. It is not moving.
Oh, is it?
Yeah.
Oh, you should have told me before.
No, I thought you were discussing about something related to.
Oh my God.
And other things, na?
Oh, is it moving now?
No, it is not moving. We thought you were discussing on the same grounds.
Oh no. Oh my God, I'm so sorry. But I don't know how did that happen.
Yeah, now now you have come out, I guess. It is in the general mode. Again, you can make a slideshow now.
Yeah, but I hope that was not. Yeah, I'm really sorry. I don't know how that happened. But oh my God.
Not an issue.
I think that would have made it difficult for the audience to follow what I was talking about.
Then if you want, you can just run through those slides quickly if someone wants to look at it.
So it was this slide where it was hung, right?
Yes.
Okay. Maybe I had this GIF. I think that would have done something.
That might have.
But yeah. Oh, it's it's very annoying.
No.
Okay, so
take a slide view now. Just check whether it will go to the next slide.
Is it going to slide 23 now?
Yeah, it is on the 24. Yeah, it is going now.
Okay.
Yeah, it is moving now. Yes, thank you.
Yeah, really apologies, everyone. I wasn't aware that the slides were not moving. But I hope you were still able to follow what I was saying. I will quickly run through this. So this was when I was talking about the shifts in the regimes. And then I spoke about how climate can cause these shifts in the regimes and disturbance in hydrological systems. And then I was giving example of one example from Southeast Australia, where we were able to model the shifts in the regimes. So I have intensity of drought here on the y-axis. And before this drought happened, all the intensities were in the first state, which is state 1. And then when this millennium drought happened, we were seeing more intensified values as shown in the pink plots, in the pink dots here. So we could see that the regimes were pretty different. Again, just adding to the fact of non-stationarity, saying that all these could not be explained from a single distribution. The distribution was changed because of the changes that happened during this millennium drought period. And then I spoke about flash droughts, and I was particularly talking about this figure here, where we show that flash droughts can onset in just a matter of a few days, 10 to 15 days, which is pretty less. And then I was talking about compounding and cascading events. So I spoke about droughts followed by bushfires, droughts followed by heat waves, and also droughts followed by flood. So I was giving an example here for the state of Victoria in Southeast Australia, where in 2023 for July, August, September, we were in droughts, but then in the month of October, we had heavy rainfall. So just, drought and then flood. So just explaining the whole spectrum of different extreme events that we're seeing and how they are sort of getting more intertwined with the complicated climate. And then this was just the take-home message. So I was just trying to, I think you heard me there. So I was just trying to, again, re-emphasize that we need to be more climate informed in terms of the policies and the governance that we're having with respect to water infrastructure and water management. And yeah, I guess I was just almost done with this slide. And I was just trying to come to this one where I'd also talk about the future directions. I spoke about the nature-based solutions as well, which I think are a really good way forward. And yes, in terms of the future directions, we've got this AI and big data as one of the big things that's happening. And definitely I see potential in that to sort of cater to the water management changes that we would definitely have going forward. And then citizen science and increased participation of citizens to help us monitor these events on the ground. And yeah, so trying to bridging basically all the science and policy gaps so that we can have better governance, we can have better water management policies, especially catering to the hydroclimatic extreme events. I guess I'm going to stop here and yeah, open to questions now. Thank you so much. And again, apologies for the technical glitch.
Yeah, thank you so much. No, we thought that you were discussing on the same grounds, and you were talking something about takeaways and other things. Very nice presentation, and something that is more oriented towards the future climate change and related to hydrology. I feel civil engineers and the hydrologists would be loving the presentation that you have done. Thank you so much.
Pleasure.
The floor is open for discussion now. Any doubts or clarifications? Please go ahead and clarify your doubts. I'll just unmute all the participants.
So yeah, I can see the questions in the chat. Maybe I can start answering them.
Yes, go ahead.
Yeah. So how water security affects the economy and society? I think like the so the main kind of crux of what I was trying to present today is to state that water security does definitely has an influence on economy and society. Water scarcity, for example, like in terms of droughts where we don't have enough water, we would let's say being an agricultural driven economy in India, we are likely to have failed cropping seasons, which would lead to economic losses for the farmers as well as for the whole nation, because we also export crops. So yeah, basically the economy would get affected primarily from an agricultural drought taking place. And society, yes, because again, if I talk about water scarcity caused due to droughts, or because of poor management of water also for that matter, society would definitely be affected, especially people who are more vulnerable. So societies where people do not have access to alternative means of water, they would have water shortages causing disruptions in their routine day-to-day lifestyles, and yeah, so that can really have a lot of socioeconomic footprint as well. What proportion of Australia is agrarian? I don't have a fixed number, but I can see if I'll try to see if I can draw here. So there's this belt here in Australia, which I'm trying to plot, that is basically the agricultural hub. So this is a very famous basin called the Murray-Darling Basin, which is the heart of the Australian agriculture. So this basin is extremely important in terms of the agricultural outputs, and a lot of agricultural activity takes place here. And then there are some agricultural lands in this part of the southwest as well. But yeah, mostly it's the south part, which are agricultural regions. I don't have a percentage, but maybe I can look that up later. But yes, that's primarily the Murray-Darling Basin. We've got two rivers here, the Murray River and the Darling River, and they form a big basin here, which is pretty agriculturally active.
Yeah.
How are the droughts being addressed? Vinay, can you be more specific as to what you want to ask? Do you mean like are we um, how are we assessing droughts?
Madam, I just put the question back again. I hope I'm audible. I'm
Yes, yes,
Vinay
you are.
speaking here. So my question was, you have quite a bit of area under agriculture there, and probably you would be facing droughts in those areas, probably the agriculture droughts or even the climatic droughts. So in case of agricultural droughts, how are you addressing that one? Like, what are the other sources or what are the ways in which it is being addressed?
So usually when the rainfall fails, people tend to extract water from the ground. So that's called groundwater extraction. That is also quite a practice when when you don't have rainfall being serving as a source of water for the crops. So what usually happens is like we've also got like good amount of groundwater bores, so people extract water from the ground, and in a lot of other cases they have built a lot of reservoirs. So reservoirs are pretty well modulated here in Australia. They are able to forecast stream flows and the inflows to the reservoirs, so they have a better grip on the outflows from reservoirs and hence the storage. So usually the reservoirs that are there, particularly in the Murray-Darling Basin, can help in case if there is a requirement from the agricultural point of view which is not met by rainfall. The other thing that I would like to point out here is, and it's actually quite a good question. Unlike in India, where we've got a lot of manual irrigation happening, in Australia, most of the irrigation, pretty much like most of the irrigation, is actually rain dependent. But there is an increase in people using sprinklers and other manual means of irrigation as well. But by and large, it's mostly rainfall dependent. So yes, if the rainfall fails, they have to look at sources like groundwater or reservoir storage. How accurate are GCM models in predicting? Vinay, did that answer your question?
Definitely, definitely. Yeah. Thank you.
How accurate are GCM in predicting regional climate changes? Well, global climate models are not very good in terms of doing regional model change projections, because global climate models are very coarse, and they do not resolve macro or micro level convective processes or other processes that govern the water cycle. And so what usually is a practice is people run a GCM, which is the regional climate model, and this is forced by a global climate model, one or several global climate models. And so the regional climate model then gives you a better and more spatially fine resolution estimate of water availability or precipitation, temperature, and other variables. But if you are if you're directly using GSM output for, let's say, a very small basin of interest to you, there is a lot of uncertainty in it. So it's usually good to do a regional downscaling of it, and then use it for whatever purpose you need it for. But yes, the accuracy of GCMs would definitely be in question if you're dealing at a more local scale. What traditional water conservation systems can be revived to fight droughts? That's actually a very good question, and I don't think I'm an expert in that one. But I think having more means to recharge groundwater, I think is really helpful, because these systems are all interconnected. Streams are interconnected with base flows and the groundwater system. So having bunds or having some sort of farm based infrastructure, if I may put it that way, to sort of ensure more percolation of rainfall whenever it falls, That is, I think it still is considered a traditional way, but goes a long way even in the present time to help conserve water. I really can't think of a lot of other ways in which some traditional practices have been continuing and have been shown to be efficient. But maybe like, having forest, having more, less concrete and more pervious surface so that you have more infiltration. So less urbanization would definitely ensure that, we've got more water reserves. And then I don't know what else. But yeah, I think we've also had like some examples of rainwater harvesting, which I think is pretty old age as well. So whenever there is rain, people would harvest it in the form of, some big tankers or big wells, and then they would store water. And that would store water for periods where you don't have water. How can communities balance economic development with long-term environmental protection to ensure resources are available for future generation in rainfall? That's actually the big question. How can we still have economic development and yet, be more sustainable in our approach? So yes, I think with respect to water, because I'm a hydrologist, I can only say that it's important to have a more regulated water use, which is sustainable. We should sort of making sort of judicious use of the water, trying to have more integrated water resources management in place so that we can, recycle the water and reuse it as much as is possible, so that we're not overly dependent on extra surplus of water coming in from rainfall or from, surface water bodies. So yeah, I guess it's just the whole different, like the idea of sustainable, sustainable lifestyle and sustainable economy, so that, we do not extract a lot of water, let's say from ground, in case if there's a drought, because we already have, enough water stored while it was raining. And so we're not sort of, just to sort of, let's say, offset the surface water deficiencies, you're not depleting groundwater, because groundwater depletion would again have other ramifications. That groundwater also has, like, ecosystem services by feeding again into streams. So yeah, I think the idea of having more integrated water management and more judicious use of water, more conservative use of water as much as possible would go a long way to ensure that we continue to have this resource, especially because freshwater resources is extremely limited for the planet Earth. How droughts disrupt ecosystem because of loss of biodiversity and ecosystem services? Yes. So an example of how droughts disrupt ecosystem services is, let's say, stream flows. So I deal a lot with stream flows because I like playing a lot with stream flow data and seeing what stream flows can do and what they're doing. So stream flows have a lot of ecosystem services. What I mean by that is, like, stream flows, ensure aquatic life that's within the streams. So for example, the flora and the fauna, for example, some fishes. So some fishes might be very sensitive to the quantity of water that's available as well as the quality of water. So if there's a drought, the quantity of water will come down, and often the quality will also come down because the quantity is sort of governing the quality. And so in that case, the pollution that's there in the streams can lead to the deaths of the aquatic aquatic life, and then also have an effect on the aquatic biomass, the plants and other species that might be dependent on it. And so you have this whole impact on the biodiversity, especially within, under the water. So that's an example from stream flows. The other example is, let's say, rivers, for example, the floodplains. The floodplains are usually, they have this alluvium, which is an important, is important for agriculture as well, right? Because it's fertile land. And so if you have droughts and if you don't have the, the normal cycle of the river where it floods and then again goes to its normal level, it can affect the agricultural productivity of the adjoining regions. And so agriculture and other, so the natural ecosystems might be getting affected by those kind of changes. So yeah.
Any government schemes are there now, updated schemes for this?
I won't be able to comment on that because I'm not so well versed with what's happening at the moment on ground in India. I've been I mostly deal with research in Australia. Most of my research is funded by the Australian government. And I am not very aware of the schemes in India, but if anybody else is better able to comment on that, please feel free to do that. But yeah, I think there have been some schemes, yes, but I'm not very updated.
Okay,
sorry.
Thank you.
What governance frameworks and institutional collaborations are necessary to effectively integrate climate adaptation strategies into water resource management? Yeah, this is a fantastic question, and this is really important. Climate change is very, very interdisciplinary, and I cannot emphasize that enough. So there is a need much more than than previously existing at the moment to do more collaboration, to understand what can really serve as effective measures for especially water availability and climate adaptation. So what I really feel would go a long way is for example, researchers and for scientists to sort of work more closely with policy people, because we want to make sure that whatever knowledge that we have about the science of this whole climate change and climate adaptation that's needed should definitely be communicated to people who are responsible for policies. And so there's an increasing role of people which are called knowledge brokers that help link the policies or people in power to sort of work more closely with scientists. And also scientists need to work more with the local people, because also I feel there's a wealth of information and wealth of knowledge in terms of the experiences that local people have, how they've been fighting climate change, or how they've been, experiencing, how they've been sort of, managing extreme events on their land for so many years. So the local knowledge needs to be integrated into the science as well. And I can speak for Australia. Here in Australia, we're doing a really good job by talking to even people who are Aboriginals, people who have been in connection with the land for like millions of years, and they've been passing on that knowledge to to generations. So their information and their knowledge about how the land, how the flora, fauna have been existing here in Australia, and how climate change is sort of linked to it, that knowledge has now been leveraged upon to understand how we as climate scientists or we as hydrologists can actually understand the changes in the climate and can then advise policy people or people who are working, let's say in NGOs or working at the ground, at the grassroots level, to understand what might work from them, for what might work for them, or let's say successful stories of how water management has been been proven to work well for some hydroclimatic extremes. So yes, there is a really pressing need for a holistic team to work together. And so people from different scales, local, regional, national, should work together. There should be, like in this particular case, because I'm talking more about, droughts and hydroclimatic events, we need to talk to agricultural, stakeholders. We need to talk to people who have experience in water management, people who are running NGOs, or people who are more involved in, dealing with these problems at the grassroots level, as well as people like scientists and other, project chief investigators who have a better grip on the knowledge of climate change. So yes, it's it's a very holistic way forward.
Yes. We shall take the last one, considering the schedule. Dr. Chandrasekharappa, you can go ahead and ask, sir.
Good afternoon, madam. It is wonderful sessions. And with respect to the water resource management, I'm Dr. Chandrasekhar, working as an assistant professor in BMS Institute of Technology and Management, Bangalore. Basically, I'm a geologist. I work for mineral exploration and mining industries and for water resource management. So the thing is, due to a rapid urbanization, most of the metro cities, especially if I would take it as a Bangalore city, when we used to get the groundwater at 30 feet or 40 feet with an open well, used to get in 20 years back, good amount of groundwater. So now that has gone down up to the 600 feet or 1,000 feet behind that, even though you're not going to get the water. Right. This is because of urbanizations, rapid urbanization and complete deforestation, I would say it is, right? So this is a scenario of the Bangalore. How could we be in the Australia? It's my just good asking the question.
Sorry, how can we?
How it is in Australia.
You mean the groundwater
Yes,
scenario?
groundwater level has got decreased drastically, or it is stable since 20 years. How it could be? Because climate change, because of that's deforestations, urbanization, and so many things, industrializations. How it is in Australia, madam?
Yeah, so in Australia, it has fluctuated a lot, particularly during the Millennium Drought period. So the Millennium Drought period that happened starting from 1997 up till 2010, the groundwater was severely depleted.
Oh.
Yes, and like it was unprecedentedly low. We also observed disconnection of groundwater to surface water in some places. And for several years after the Millennium Drought, when the rainfall was back to normal, groundwater and stream flows had not recovered. And so some of the catchments which experienced that drought are still recovering. Yeah, I think here in Australia, particularly, a long drought definitely influences the fluctuations in groundwater, and they can take several years to recuperate and to come to normal levels. Yeah.
Right.
And with the GRACE figure that I showed, so the GRACE satellite data, I'll go back to that slide. Yep, this is so the GRACE trend data is basically showing how the surface storage has changed. So surface storage would include groundwater storage as well.
Exactly.
So over Australia, there is not a lot of change for the south part, but then the northeast, the northwest part has shown a decline.
Yeah. Thank you very much for this wonderful information. Thank you.
Yeah. I conclude this particular session by wholeheartedly thanking Dr. Goswami for spending her valuable time. I hope this would be a better day now because you might be having holiday tomorrow.
Yes.
Yeah. So nice of you to join us and deliver such an informative session. And we hope to have a similar kind of knowledge sharing in future days also.
Sure. Thank you again, Professor Chandrasekhar. This is a really good opportunity, and I had a good time interacting with the people here. Thank you. Yeah. Thanks everyone for joining and for listening.
Thank you. Thank you so much. Have a nice day.
Thank you.
So we have our next speaker with us. You are there, Nathaniel?
Yes, I'm here. I hope you can you see my slides?
Can you share it?
Yeah, I've shared it.
Kindly run through the second or third slide just to check whether it is working properly or not.
Can you see the second slide?
Yes, yes, it is working properly. I'll just introduce to you to the audience, and you can start. Good afternoon to all the participants again. So we have one more excellent speaker and also expert in the area of safe reuse of treated water. Nathaniel possesses a significant expertise in the water use and safe reuse of treated water, demonstrated through his professional roles and key points. As a consultant, as a senior research scientist, and as an associate director currently at New Gamma Consultant Private Limited, New Delhi, he served as a technical expert for municipal wastewater, playing a crucial role in policy analysis and co-creation of state policies for Uttar Pradesh, guidelines for Uttarakhand that align with the national framework for SRTW. SRTW, as it is been mentioned here, safe reuse of treated water. He also conducted feasibility assessments for SRTW in Haridwar, developed SRTW business model, recommendations, solution documents for Panipat, and comprehensive SRTW Compidum incorporating European Union approach. His work involved leading stakeholder meetings, collecting data for Panipat solution documents, and supporting international exchanges on monitoring SARS-CoV-2 in wastewater. His extensive tenure at the Energy and Resources Institute, TERI, as an associate fellow and research associate, further established his proficiency in water and wastewater management. He was instrumental in Pavitra Ganga project, focused on unlocking wastewater treatment, water reuse, and resource recovery opportunities in India. In this capacity, he identified drivers and barriers in the governance of wastewater treatment and reuse in India, developed policy briefs, engaged stakeholders to improve wastewater management and resource recovery. He documented global best practices in industrial wastewater treatment technologies from primary, secondary, and tertiary treatments and treated effluent disposal or reuse, including an assessment of nature-based solution and decentralized wastewater management system for Bureau of Indian Standards and CPCB. Furthermore, he contributed to the environmental and social impact assessment for National Ganga River Basin Authority project, specifically evaluating STP and sewerage works impacts and developing India's environmental and social management framework. He has also provided training to Delhi Jal Board officials on sludge management. Further, academically, Nathaniel holds an Master in Science in Water Resource Management with special emphasis on water quality and pollution, wastewater management, and integrated water resource management. He has co-authored papers on perceived drivers and barriers in the governance of wastewater treatment and reuse in India. Insights from two-round DEFLI study. Received the 2024 Most Downloaded Paper Award for Resources, Conservation and Recycling. He has also co-authored publication on the management of used water and SDG 6.3, Challenges and Opportunities for India, and mainstreaming governance on wastewater treatment, water reuse and resource recovery, learning from India and the European Union. So this is a brief accomplishment of Nathaniel sir, and we wholeheartedly welcome you on behalf of Vishwesvaraya Technological University, and also from the participant side, we are very grateful to have you, sir. And the floor is open for your presentation.
Thank you so much, Chandrasekhar. Chandrasekhar and I were colleagues at TERI once upon a time. And one of the projects that he mentioned was where he was the principal investigator, the original principal investigator before he moved back to Karnataka, which was the environmental and social management frameworks, which some of the discussions which we've had, informal discussions which we've had, I can see it till today, Chandrasekhar. The discussion on having those barriers, the steel barriers, instead of having a plastic barrier for sound wall. We can see it all over Delhi and all over other areas. So a lot of impactful work has been done. I would also like to thank Pallavi, the previous speaker, for bringing out quite a few very interesting things, because climate change is indeed a cross-cutting issue. And since it's cross-cutting, I would also like to answer a few questions from the previous section where Vinay asked about what is being done to combat this. So in Australia, Vinay, they are also doing SRTW, Safe Reuse of Treated Water, driven by this millennium drought, where they ran out of water. And since they ran out of water, they were able to bring up this $1 billion TTRO plan, tertiary treatment RO plan. But similar to India, Australians also are more concerned about the history of water, which basically means that this water from the TTRO plant actually came from sewage and got refined into drinking water quality. But then, since they are more concerned with the history rather than the quality, they send this water back to their reservoir and pump it back there, which is quite a lot of energy impact. But that is a challenge also that we face on how can we change perceptions of this, of reusing treated water. So I'm going to talk to you today about the safe reuse of treated water for fit-for-purpose uses in India. I would like to introduce Mugama Consultants, or MGC, to the audience. MGC was established in 2015 with a vision to improve the quality of life of communities by applying global knowledge on environmental protection to the local context. Our mission is to create new knowledge through rigorous research, build societal capacity for environmental protection, advocate for policies that are environmentally friendly, and reach out to communities for their support for environmental causes. Achieving the SDGs is the key essence of our work. Our focus is on water and waste management, and we specialize on water quality and quantity, used water management and reuse, chemicals of emerging concern, the ecosystem, wash, circular economy, health, and riverine pollution. We are knowledge creators to address the data and implementation gaps. We are knowledge customizers to fit the knowledge to local conditions, as well as to provide targeted capacity building. We also use systems thinking to act as knowledge connectors, to blend academics and research to bring about science-informed policy changes and reforms. So stepping into the subject of discussion. So the essence of SRTW is the shift from treating wastewater as a burden to viewing it as a valuable resource by reducing the gaps between water demand and availability, removing pollutants from water, reusing this treated water, and recovering resources such as biogas. I would like to create awareness about SRTW, Safe Reuse of Treated Water, and I would like to draw your attention to the National Framework on Safe Reuse of Treated Water, which was released on November 2022, to get more support for widespread and safe reuse of treated water in India. There is a YouTube video, which Namami Ganga, we will get to that in a moment. And I would request the participants to scan and take a look at this PDF as well. The vision of this national framework is for the widespread and safe reuse of treated use water in India that reduces the pressure on scarce freshwater resources, reduce pollution to the environment, and risk to public health, while achieving socioeconomic benefits by adopting a circular economy approach. So this is the launch by the previous Minister of Jal Shakti. We will now go through that short video.
The audio is not coming.
The audio is not working, Chandrasekhar? So we'll move on then to the next slide. So wastewater is actually a broader term for contaminated water from different sources, whereas sewage is the wastewater generated from residential sources. It can be further delineated into black water, which comprises of used water from toilets, which contains fecal matter and urine. Drain water is the water from sinks, washing machines, showers, which has a relatively lower levels of contamination compared to black water. You can see I've struck out the word wastewater, and we will see in the upcoming slides why it is done so. In the operational guidelines released by MoHUA, the Ministry of Housing and Urban Affairs in 2021, for Swachh Bharat Mission Urban 2.0, the term wastewater is replaced by used water. As per the analytical brief of UN Water on wastewater management, it is defined as the combination of domestic sewage, contaminated water from commercial establishments, industrial effluents, and the effluent from agricultural reuse.
The slides are not in the presentable mode. Kindly present it. Share the slides.
Sure. Let me just... I'll just go back to the previous slide.
Yeah, now it is visible.
Just give me a second, Chandrasekhar.
Yes.
You can see the slide now. This was the previous slide.
Yes, it is visible now.
Perfect. So we move on to the next slide. So recycled or reclaimed water is defined as fit for purpose, used water that can be used under controlled conditions for beneficial purposes, either within the same establishment or industry or for irrigation or for different areas as well. Whereas what water reuse refers to the use of untreated, partially treated, or treated used water. You can see that the National Framework for Safe Reuse of Treated Water has also adopted the term used water instead of wastewater. This was done to signal a shift away from the connotations of waste, as it is a resource and not a liability. We need to adopt the use of the term treated used water, or the acronym TUW, which captures the focus of safe reuse and treatment that is fit for purpose. So building on the successful example of Singapore, which uses the term NE water for their used water, for their treated used water, and change public perceptions. The term Apna Jal, which translates to our water, captures the notion of safe and beneficial use of treated used water, implying that it is a commodity that can be used beneficially. So SRTW is a part of the larger river basin management framework that India is shifting towards. We were lucky to be a part of the process in 2018-19, where we introduced the EU Water Framework Directive to officials in India. Through the training program, we introduced the EU Water Framework Directive, and then the policymakers identified several program of measures, and there have been several improvements since then. On the image to the left, we can see that there are a variety of types of uses in the European Union due to the diversity of needs. So similar to the EU situation, the SRTW policy also accommodates a diversity to fit the states across India. But we can see that the perceptions in India are changing, and this national SRTW framework provides guidance to states as well as an implementable framework for national support programs. And to ensure that SRTW is sustainable, new business models are being developed and implemented across the country. There are also other complementary national processes and programs that support safe reuse of treated water. As we can see, several states have adopted reuse policies. Hopefully, by the end of the year, there will be more states with SRTW policies. At MUGAMA, we are actively supporting the development of the new SRTW policies for UP and Uttarakhand, for Uttar Pradesh and Uttarakhand. And we are very hopeful to see these come up and about before the end of this year. When discussing about safe reuse of treated water, the key SDG here is SDG 6, which is about ensuring availability and sustainable management of water and sanitation for all. The key words here is for all, because if we leave, we are not supposed to leave anyone behind. We can see that for SRTW, the target 6.3 is the most relevant SDG target here, which is about improving water quality through wastewater treatment and safe reuse. However, there are several challenges with billions of people still lacking access to safe drinking water, sanitation, and hygiene. There are about 23 billion people living in water-stressed countries. And when we take a look at our natural wetlands, the global natural wetlands, which have shrunk by 35% in 45 years, which is thrice the rate of forest loss. We can see that the progress for SDG 6 in particular is relatively slow, with around 129 countries not being on track to achieve SDG 6 by 2030, which means that the current rate of progress needs to double for us to achieve it. So let us look at the various reasons as to why safe reuse of treated water is crucial. One is the safe reuse of treated water. It directly addresses the challenge of water scarcity. It increases the availability of water supply and helps achieve sustainable and equitable distribution of this vital resource. With increasing urbanization and industrialization, the demand for water in various sectors is also rising. The reuse of treated water can be a very viable strategy to meet this increasing demand. The implementation of SRTW also will significantly reduce the pollution load discharged into rivers and water bodies. This will improve their health and protect aquatic life. We can also see that the reuse of treated water, it not only addresses water needs, but also contributes to the economic growth of urban local bodies, which are usually cash-strapped. It aids and provides opportunities for revenue generation, which is very important for them to sustainably provide services to the urban population. As we've seen that, yes, our wetlands are shrinking, treated water also provides a potential scope of replenishing both surface water bodies and groundwater bodies, specifically through indirect recharge, with a lot of safeguards for groundwater. We'll discuss that in a bit as well. So we also see that untreated used water is a menace to the environment and public health. So safe reuse of treated water is a possible solution to safeguarding public health and environmental health. So water resources are already stressed in India, and I come from Meghalaya, where water stress is seemingly less, but I can attest to the fact that all regions in the country faces this issue of water stress. My father is from Cherrapunji, and Cherrapunji, which used to be the region which receives the highest rainfall in the world, it there are frequent droughts, especially during the winter and other dry seasons as well. With increasing population and aspirations, there is going to be like higher demands from competing sectors. We can see here that there are various projections. Yeah, I would like you to draw your attention to the number 1447 BCM by 2050, which is by the standing subcommittee of the former Ministry of Water Resources. We have to keep in mind that the utilizable water resources, including both surface and groundwater, is only 1,123 BCM, which indicates a bleak situation in the future. We can also see that that the price for bulk water is increasing, which is also increasing financial stress. So poor water services can also result in high burden of disease, indicated by this slide here. And UNICEF estimates an economic burden of approximately 600 million USD a year in India. And we have seen through our experience of the COVID-19 pandemic, we've learned that disease can impact anyone. Hence, there is a need for collective action to ensure that the most vulnerable are safeguarded. So this graph shows the capacity gap in wastewater treatment in Indian cities. And there is 38 MLD amounting to 63% of sewage generated that is left untreated. So SRTW also offers a scope to recharge lakes and wetlands. The photo of the lake is of my last visit to Porur Lake. This is where Chennai Metropolitan Water Supply and Sewerage Board is implementing a very interesting indirect domestic reuse from water release from their 10 MLD tertiary treatment plant in Nisa Pakam. And they call this water circular water. So, as I mentioned, urban local bodies are usually cash-strapped. Circular economy, safe reuse of treated water, provides a revenue stream for treatment. And additionally, the recovery of nutrients supports agriculture by reducing the need for fertilizers to be added. Like this is a image depicting the business model that SMC, Surat Municipal Corporation, has been implementing. It is a wonderful example of how ULBs can generate revenue. SMC has been operating this 40 MLD sewage treatment plant, which is based on ultrafiltration and reverse osmosis at Bumroli, where it generates industrial grade water and supplies it to Pandesara GIDC, and it has been doing this since 2014. This also means that they have the funds to improve used water treatment and recycling, and the industries are assured of good water quality for their processes. So the national framework sets the context and priorities for the directions of safe reuse of treated water. It gives us a pathway of mainstreaming the safe reuse of treated water by encouraging states to adopt the necessary enabling environment, and as well as actively promoting its implementation. It also views SRTW as a part of the wider water circle, which encourages multiple cycles of use and reuse. It also supports a commitment to the achievement of SDGs Target 6.3. To prevent any confusion, it also provides clear defined roles and responsibilities of various government entities and agencies, as well as those of other key stakeholders such as industry, other parts of the private sector, local government, civil society organizations, and citizens. It also looks to establish new funding mechanisms and support synergies among central government programs, And as I mentioned earlier, that SRTW is part of river basin management. And here it means that you can include the potential of SRTW within the catchment water cycle and use it to clarify entitlements to water. There are several states that are trying to use this to their advantage as well, wherein they supply treated water and request for more water to be allocated to them from upstream locations. So the SRTW policy covers non-potable reuse in urban and rural settings. It provides the mandate for safe reuse of treated water, provides a mechanism to support it through the provision of incentives, and it also provides a model framework that states can use in the development, as well as to enhance their existing reuse policies and other regulatory and implementation instruments. So here we can see that the source of water for SRTW is the purple lines. Used water generated by households and commercial enterprises in both urban and rural settings is the source of water for SRTW. We are not talking about industrial use water, which is covered under a separate ZLD initiative by CPCB. And there is special considerations required, especially in areas where there are industrial use water being mixed with municipal use water. And the priority here is to ensure separation. So some of the potential sectors identified for the reuse of treated use water in the national framework are the following. In the industrial sector, treated use water can be used in industrial estates for various industrial processes, for power generating facilities, railway operations, and other uses as well. In the agricultural sector, it can be used for irrigation, forestry, horticulture, and aquaculture. But there needs to be several checkpoints for this to ensure that chemicals of concern and elements of concern do not reach our food basket. Treated use water can also be used for municipal uses, such as landscaping, toilet flushing, as well as firefighting. The environmental uses of treated water include its discharge into water bodies, which helps to maintain wetlands. And I hope that you remember that wetlands have shrunk globally by 35%. So this is one of the ways that we can help regenerate them. In the construction industry, we can use treated water for various construction related activities. However, there are various water quality aspects that need to be met, specifically for concrete mixing. The quality of water must fulfill Indian standards, which is IS 456 for plain and reinforced concrete. This will ensure structural integrity of construction. Aquifer recharge should be kept as the last priority when there is no alternative for use of treated use water. The level and quality of treatment of treated use water and the method of recharging groundwater will need to be determined by states during the finalization of their respective policies. There is no direct aquifer recharge, but indirect aquifer recharge is allowed through the framework. SRTW is very context specific, with states having different endowments of natural resources, variations in levels of urbanization, industrialization, and rural economy, as well as states have their own development priorities. So neither is the situation within the states homogeneous, with many districts existing that can be characterized as waste scarce or water rich, contrasting with the designation of the state as a whole. NITI Aayog has released the document on reuse of treated water in urban peri-urban agriculture in 2023. And it can be used as a reference document. We also need to ensure that farmers don't lose out and get benefits from this policy. So the pricing of treated use water should consider the ability to pay, as well as alternative sources of water. One of our projects was to assess the presence of endocrine disrupting chemicals in the food and water basket of India, and the use of untreated water or partially treated water for irrigation is a potential pathway that can introduce these chemicals of concern to food and water, thereby threatening public health, especially since very minuscule amounts of some CECs can impact our endocrine system. Hence, it is very important to address prior use of untreated wastewater in agriculture and to explore mutually beneficial outcomes. Again, indirect aquifer recharge should be the last priority for reusing when there are no other potential uses for it. There is also a call for a risk-based approach with stringent monitoring and treatment measures to be implemented. And this is because treating contaminated aquifers is very difficult, very expensive, and it can cause multi-generational impact. So the SRTW framework had anticipated that all states would adopt and start implementing a state W policy by the end of 2022. However, the progress has been slow, as I've shown earlier in the previous slides. Apart from this, it had also anticipated that states that are already having SRTW policies, they would review them within the same time frame to incorporate any relevant policy provisions necessary to satisfy eligibility criteria for national support programs. Like, states are also expected to set targets for 100% collection of used water and 100% treatment the same to enable the achievement of targets for use. So the targets are where STPs are operational and collection of treatment and collection and treatment capacity exist. Like 50% of treated used water is to be safely used by this year and 100% by 2030. In cases where STPs do not exist or are non-operational or collection and treatment capacity does not yet exist, 30% of used water is to be collected and treated and safely reused by 2030, 50% by 2035, and 100% by 2045. So to supplement statewide milestones, target can also be linked with the establishment of STPs. For example, 50% reuse within 5 years of establishing an STP and 100% within 10 years. So a situation might exist in the near future where we have universal treatment and reuse, effectively leading to zero discharge cities. This is one of the dreams and the major milestones. So the expected outcomes is like there. We know that SRTW water security must include SRTW, as we are already water stressed. So replacing fresh water use by using treated used water will reduce pressure on existing surface and groundwater resources. It will also provide health benefits due to reduced pollution of water bodies, environmental benefits by reducing contamination of surface water bodies and groundwater, and social benefits by improving productivity as well as well-being. And the view of treated used water as a resource opens up a revenue stream which would also help reduce risk of food safety risks, as well as increase the capacity to provide green jobs. Since we are moving on this way of reusing, so research and development is also expected to flourish so as to provide more efficient technologies through innovative actions. It is also expected to increase the capacity of urban local bodies in their ability to implement SRTW projects, as well as to include cross-sector collaborations. So there will also be reduced climate emissions, because if we must keep in mind that urban local bodies, the most amount of energy usage is in the transmission and treating of water. So the resulting reduced pumping of fresh water will definitely reduce emissions, as well as I was in this ETP, which is has just been recently established by Haldiram, and they are also generating biogas, and in fact they're generating much more biogas to the point where they can offset the treatment cost, the cost of treatment for the water. So the generation of biogas and the use of biogas also mitigates the production of methane from untreated water, wastewater, and thereby reducing climate emissions. With regards to water quality for reuse standards, it needs to be pragmatic and not stringent. There is a balance that is required to avoid the loss of opportunities for treated use water. And the policy establishes that wastewater will be treated to secondary level at the STP. And standards for reuse to be fit for purpose that are defined separately for each end use, which means that there is a considerable amount of work required to establish a full range of standards. However, when we take into consideration the nature of contaminants, a risk-based approach is required. But dealing with emerging contaminants will take time, and a phased approach to avoid SRTW implementation delays is more pragmatic, because there is a need to consider the current and future capacities of laboratories to carry out tests to assess if the standards are met for the defined parameters. And strict discharge norms are prerequisites for mitigating risks. And with regards to reuse in agriculture and aquaculture, they should meet standards for specific crops and aquatic species and consider food safety standard requirements for public health and trade. The quality for reuse in industry is very site-specific, hence the financial responsibility of treatment above the discharge norms beyond secondary treatment rests with the industry, which basically means that they need higher quality of water. The money to establish this tertiary treatment plant will have to come from the industry. Again, there is a need for a precautionary approach for discharge into aquifers. And we also need to consider the consequences of pandemics and risks with regards to pathogens. So, treated use water is social and environmental and economic commodity. So, the pricing principles for treated use water should aim to encourage the use of treated water over fresh water, while also encouraging payment practices. Different pricing would be needed based on the end use, with full cost recovery expected from people who can afford to pay for it, for example, the industrial sector. And the revenues generated from SRTW can cross-subsidize STP coverage as well as performance. And other incentives can also be considered, such as tax, like for people who are implementing SRTW, such as tax breaks, as well as waivers of other charges. Business models. In the first session, the introductory section on Monday, there was a talk about, like, if there is no money, if it does not make economic sense, it will not be sustainable. So business models are key for sustaining safe reuse of treated wastewater, treated used water. So while there is guidance in the SRTW framework on the selection of business models, it also establishes that the selection of which business model is a local decision. The policy also outlines various business models, including public, private, and private, and PPP, to encourage community participation in wastewater reuse. It also highlights successful case studies of reuse by industries in agriculture as well as in urban local bodies. It also states that these states should have a committee to approve business and contract models, and a risk matrix is also included to help identify appropriate mitigation strategies. Business and contract models are very, very important, because we have seen that some developers have established like contracts in ways where they make most of the money on the top end while during construction, and they can afford to, and they have very less amount of money coming in for operation and maintenance, which basically means that if there are any fines, the fines would be so minuscule and would not make an impact. So it would not drive them to perform better. So as mentioned, that there are various business models. The implementation agency shall mandatorily provide the quantity and quality of untreated or treated use water. If not, like, relevant penalties applicable on the implementation implementing agency will also be applied, and especially for private ownership, if the infrastructure or distribution of treated use water is owned and operated by the implementing agency, then the private entity responsible for treatment would require like assurance of minimum guarantee on revenue from the sale of treated use water, or the uptake of assured quantity of treated use water at a fixed price. We have seen this being done in Ghaziabad, where they are reusing water, and the Ghaziabad Municipal Commission is giving assurance to the WABAC, who is the executing entity, or who is the private entity responsible for treatment. So the safe reuse of treated water concept, like water reuse, is one of multiple options, and we need to consider the availability of used water, one, the demand for treated used water, the treatment requirements, available technologies, and the various options, and we also need to have a pre-feasibility assessment as well as a feasibility assessment to be conducted before implementing it. And the main challenge here is to find a solution with the lowest cost to benefit ratio. We can also see here in this paper by Uday and Joseph Ravikumar, who is one of our advisors, that technology requirements for increasing water quality for various purposes will usually come at a higher cost, which would mean that there will be a need for greater cost recovery to be financially sustainable. So let us look into a few case studies. So Surat is the 8th most populated city in India, and it is the 4th fastest growing city globally, which means that there are also increasing water demands from the industrial and domestic sector, which is further further complicated by the limited availability of water in the Tapi River. However, one of the things that going on well for them is the Gujarat's policy for reuse of treated water, which was established in 2018, and Surat came out with an action plan called Surat's Reuse and Recycle of Treated Wastewater Action Plan in 2019, which is very comprehensive and pragmatic. So Surat has 11 STPs with a total capacity of 173 million liters per day, with another 6 STPs augmenting this capacity by 583 MLD. The Surat Municipal Corporation has a sewer length of 1,957 kilometers, almost covering the entire population. And by 2021, it had already achieved 40%, or 747.86 million liters of reuse of treated water. So the The city's rapid population growth is attributed to industrialization in the peripheral region, which is putting additional pressure on the freshwater resources. So to address the future water demand for freshwater, Surat has been taking different types of reuse of treated use water for agriculture, gardening, road washing, toilet flushing, and for industries. So the goal of the Gujarat policy for use of treated water is to achieve 80% coverage and collection of sewage in all municipal towns and 100% treatment of collected sewage according to the prescribed standards, and reuse at least 25% of the total freshwater consumption from treated wastewater within policy limits, with 70% reuse by 2025 and 100% by 2030. So, as mentioned, reuse and recycle of treated wastewater action plan of 2019 is also supported by the fecal sludge and septic management action plan of 2019. So, what did SMC do? So first, they mapped the different locations of these STPs, the capacities, the processes used, and the type of potential for reuse. After that, they mapped the potential for wastewater recycling and reuse, and they identified various users and the nearby STPs as well. So the case study that we're going to examine here is the 40 MLD capacity TTRO plan, which was established, which was constructed by MS Enviro Control Associates at Bamroli for reuse by the Pandesara GIDC. So it has about 85.1 crore towards CapEx and 80 crores towards OpEx for 10 years. The plant treatment stages include sand filtration, ultrafiltration, and activated carbon filter. So the benefits is that 40 million liters of fresh water is now available for domestic use, since this competing demand has been replaced by the water from the TTRO. And now, couple of years from now, the cost of this treated water is around 28.58 rupees per kiloliter, which has been earning this SMC 481 crores per year. I'm not sure if the...
We are at Bamroli sewage. We are at Bamroli sewage treatment plant in Surat. Here in Surat, around 1000 MLD or million liter per day of sewage comes through around 11 sewage treatment plants. One of them is where we are right now. This plant has an installed capacity of 215. Right now, it treats around 130 MLD of sewage. We have with us Mr. Bharat Desai, is the executive engineer of the
Drainage Department of Surat Municipal Corporation.
Okay, so sir, please tell us this first process. What is it that is coming right now?
The sewage that has been collected from our household and the commercial property through pumping station and pumping main, it is first come over here. This is called inlet chamber.
Okay.
Currently, you see all the dark sewage is being thrown in this pit. From that, the first will be the screen. Whatever the particles, physical particles, floating particles are there, that floating particles will be screened from this. You can see that, and thereafter the physico-chemical process will be started. That consists of primary treatment as well as secondary sewage treatment.
So once that sewage comes to that chamber, inlet chamber, it goes through mechanical screening, where all the other particles like plastic materials are sorted out. Then it comes to something called a grid chamber.
the heavy particles that is called grit is also coming with this sewage, and in this it will be settled, and with this screw mechanism it will be separated out and taken out. It is separated, and you can see at the bottom it is getting collected, and through this tractor we are disposing to this Khajot disposal plant.
So once the process of separation of grit takes place, the water comes to the different chambers, and here there are 3 processes involved.
In these 3 processes, whatever is the one is filling, and you can see here, first the aeration will be provided. Okay. After the aeration, this will be settled in this. So this is stagnant water, and in that last is a decanting, the water will be taken out. Okay. All entire biological process takes place in one single chamber instead of different chamber. That's the reason how you can save the space.
मेरा नाम है प्रियेश मगजवाला, मैं यहाँ का प्लांट इंचार्ज हूँ। यहाँ पे जो ये पूरा ट्रीटमेंट फैसिलिटी इसको बोलते हैं सीक्वेंशियल बैच रिएक्टर टेक्नोलॉजी। इसमें जो एयर रहता है इसमें बायोलॉजिकल प्रोसेस होता है, तो बायोलॉजिकल प्रोसेस में फूड माइक्रोन रेशो FM रेशो जो बोलते हैं उसको मेंटेन करना पड़ता है। तो इसमें जो एयर देने का मकसद ये है कि जो बैक्टीरिया रहते हैं बायोलॉजिकल, तो उसको जिंदा रखने के लिए आपको बाहर से ऑक्सीजन देना पड़ता है। तो इसके लिए हम उनको एयर देते हैं, जिसके कारण वो बैक्टीरिया जिंदा रहते हैं, और बैक्टीरिया जो है वो अपना जो सुएज वाटर है उसमें जो स्लज है और उसको ऐसे फूड वो खा जाता है।
Now we have come to the UV chamber. Here ultraviolet rays are going to be used to kill the bacteria over here. And
coliform bacteria, so that nothing will remain in this. All the whatever the bacteriology, something is left out, it is also cleared here. Okay. And secondary process is completed at this end. Okay. You can see the water is taken out from the UV chamber.
So this is the water.
This is the water. You saw the first water there, yeah. And now this is the secondary treated water.
This can be released into the.
This can be released in the river as well as creek.
Okay.
The nature water course is available, because we are treating as per the Pollution Control Board standards.
Okay.
We are in the UV control room. Whatever the water is being treated, there are certain parameters as per the Pollution Control Board that will be observed online on this, and that is connected with the Pollution Control Board. The data is directly fed to their area. So even Pollution Control Board also can come to know what are the disposal parameters available in this plant.
So they say a lot of energy is used in running this kind of a plant. So don't you think it's like a dichotomy here that, you know, once you're trying to clean water, but the energy is also getting utilized, and that energy is coming from somewhere. So what have you done for that?
So as far as the sewage plant is concerned, whatever the sewage gas generated after the due process, that is normally to be flared up from this, you can see that is the flare provided. Now what we did, that we have provided gas engine into it. We are using that first into that gas. That gas is going to scrubber where the H2S is removed, and whatever the pure methane is extracted from that we are feeding into our gas engine, and from this gas engine electricity is generated. That will provide around 30 to 40% electricity demand of the plant itself.
So 3 megawatt is the total demand, and 5 megawatt is
0.5 megawatt.
0.5 megawatt is what you kind of generate from the
a plant. That is around 10% right now, but it will increase up to 30%.
In the third process, where the tertiary filtration started, we went to the disc filter. Once the water goes to the disc filter, it then comes to UF and RO, ultrafiltration and reverse osmosis. And the water that we saw at the start of the video will look something like this, and let's see if it's something that we can consume. We can actually say that we are having sewage treated water. It's fine. I don't know if I'm going to get ill after drinking this.
No, nothing, not at all. Rest assured.
Thank you so much for watching this video. We'll bring you more such videos. Give your suggestions in the comment section. Keep watching this space.
So, because of the success of the Bamroli TTRO plan, Surat Municipal Corporation has started building another TTRO plan at Dandoli STP, which can treat an additional 40 mld of water using the same technology, the ultrafiltration and RO technology, which will also augment the reuse of treated water to a total of 80 mld, because there has been, since they have had a good experience since 2014, they are receiving assured supply of good quality water. The industrial estate is coming back and requesting for more of this water. Similarly, in a nearby GIDC called Sachin GIDC, they have also requested the Surat Municipal Corporation for 35 million liters of treated water. And therefore, another 35 mld of tertiary treatment at Bamroli using the same technology is also being implemented to cater to the demand. As you can see through their demand mapping, right? Surat is using water for industrial processes. One, because the industries are the one who will pay, who can afford to pay. They are also using it for gardening, agriculture, road washing, as well as sewer jetting machines, flushing, as well as there is this new dream city, the Surat Dream City. They are also planning to use it for commercial use in the Dream City. But we should also learn about the challenges faced by the SMC. So they have shared that the variation and fluctuation in the quality and quantity of sewage, particularly like there is a challenge to ensure that no industrial waste is mixed with sewage, has been the key challenge. And another challenge which they faced was the requirement to maintain a steady supply to the TTRO. So to address this risk, SMC had implemented a buffer tank as a solution to this risk. Another challenge which they faced was the requirement for uninterruptible power supply for continuous functioning of the plant, because biological processes can tend to be disrupted. And there is also a comprehensive need for proper treatment of the reject water that arises from the tertiary treatment plant. Comprehensive operation and maintenance is up to the tertiary treatment plant is also required. This stems from the secondary treated from the STP to ensure that it meets the inlet parameters required for the TTRO. Since most of the on-site components implemented in the TTRO were imported, so staff training is a must. It is a must so as to avoid dependency and to build an in-house capacity so as to remove this dependency on external forces. So the learning from the Surat model is such that we can see that the Surat model was successful and it can be adopted across other urban local bodies, which can stem to benefit from one, the structured approach of identifying first the availability, checking for the potential demand of treated water, and then establishing these MOUs, these agreements for supply with industries. And this would have amounted to nothing if it wasn't coupled with the availability of funds for CAPEX, as well as the ability to meet operation and maintenance costs, as well as generating profits. Generating profits is of extreme importance when you're trying to look at scaling up efforts for reuse. So this success of SMCs has reduced Surat's dependency on Tapi River, resulting in an increased supply of fresh water for domestic use. The reduction in surface and groundwater abstraction Along with this reuse of treated sewage, the treating of the sewage has improved the environment, the water quality and the environment and the water security in the region. As I had mentioned before, that most urban local bodies in India, they struggle to secure funds, and they usually are dependent on financial support from either the state or the central government, which basically means they are not able to sustain themselves. So, but this augmentation of revenues through the sale of products such as treated used water, maybe soil conditioners, biogas will definitely help urban local bodies be more self-reliant, as well as to be able to look forward, plan for the future, expand their activities, and this can only be based on the more reliable funds which are now available. Moving on, we're going to talk about the case study in Chennai. So Chennai is the capital city of Tamil Nadu, and it has a population of about 74.38 lakhs, and they are living in about 426 square kilometer of the corporation area. And the city generates about 1,199 million liters daily of used water. And Chennai Metro Water Supply and Sewerage Board, or CMWSSB, is the responsible entity for providing water supply and sewerage services to the city. The sewerage system in Chennai city is also divided into 5 drainage zones, and these zones function as macro systems covering entire cities, and they have independent zonal collection, conveyance, treatment, as well as disposal facilities. We have seen that Chennai is very reliant on groundwater to supply its water requirements. And this is being replenished by lakes and groundwater. And we've seen that they have struggled. While the annual rainfall is about 1,400 millimeters, we have seen that there have been several droughts in Chennai, and they have struggled to meet their water demands. And to meet their water demands, water supplied through desalination facilities and Nemali and Minjur and Kaveri from Viranam, Krishna River from Andhra Pradesh, Pondi Reservoir, the lakes at Red Hills, and other sources. So while the demand is about 1,200 million liters, Chennai currently gets around 985 million liters from various sources. So to stem this gap and to fulfill the demand and decrease the existing water stress, reuse of treated water was started. And we will see that CMWSB, which has established this tertiary treatment TTRO facilities at 2 locations, Coyambadu and Kudungayur. Forgive me for my pronunciations if they're incorrect, with the capacity of 45 million liters per day to address the raw water requirements of industrial regions. So this TTRO project was required to address the competing demand from both domestic, agricultural sectors, which might hinder industrial expansion. There is groundwater and surface water depletion owing to over abstraction and contamination from untreated used water. And there is an increasing danger of drought. Hence, there is a need to preserve these existing water resources as well as to supplement them. Every year, we've seen Chennai having severe water shortages, and the cost of water delivered by private tankers is quite expensive, but the quality and quantity are not reliable. Hence, this was created, the treatment of used water was created in order to safeguard these existing water resources and enhance hygiene and sanitation conditions as well as to generate income for the board. We are going to take a look at the 45 MLD capacity TTRO plant at Coimbatore. This project was executed by WABAC IDE Consortium, Chennai, with a capex of 396.5 crores and 197.56 crores towards the OPEX cost for 15 years. The TTRO plant and transmission mains for conveying this treated use water have been established, and these storage tanks are at Palikam, Valam, Padangal, Arangadam, and this is further supplied to the Sipcot industries located at Irumgatu, Kotai, Sirupuram, Budur, and Oragadam by Sipcot. So the consortium delivers this water to these storage tanks, and they are paid, if I'm not mistaken, they are paid about 45 rupees per kiloliter. Excuse me. But since Sipcot is responsible for transmitting it, they charge these industries rupees per kiloliter, and it earns them about 19.67 crores of revenue as well. So we are going to try and see if we can run a video of the TTRO plant to the Coimbatore. And they also use ozonation So as we saw that challenges to safe reuse of treated water still exists. In the previous video, you did see the reporter from Economic Times asking the official that mere ko kuch nahi hoga, because he drank the RO water, the treated used water. So there is a definite need to change, to enhance awareness and to change public perception. We need to also change how we think about used water as a resource. Apna jal, our water, treated used water. And this is not just a challenge that is being faced by us in India, but we have seen it in other countries as well, where people are more concerned about the history of water and they're not as bothered about the quality of water. But there is, just because there is an STP, doesn't mean that there is also a demand for treated use water. So for STP, for safe reuse of treated water to be viable, there is a need to match the demand for this treated use water to ensure that, one, yes, you are able to treat this water and supply it and also get paid for it. So financing is a key, it's a key driver as well as a key hindrance. There should be incentives for widespread uptake as well as disincentives for those who aren't taking it up. Disincentives such as there are other provisions in the SRTW policy which talks about no freshwater zones, which is very important for regions such as the Gangetic Belt, which is often viewed as water-rich states. Yeah. So if there are no freshwater zones, which basically means that industries are not allowed to uptake freshwater, be it from groundwater or surface water, but are mandated to use treated use water, then this no freshwater zone could potentially bring about a change in perceptions. There is a need to comply with standards, not just standards in terms of quality for use, but also standards with regards to being able to mitigate other risks such as climate vulnerabilities, energy vulnerabilities. Since the safe reuse of treated water, you can see that it has varying uses, right? From agricultural to industrial to energy. So which also means that there will be a number of departments and ministries involved from the central level to the localized level. And there is a need for synergistic work rather than to work in verticals, in their own verticals. So to enhance coordination. And we have seen this when we were introducing the EU Water Framework Directives. We've had these policymakers from various water departments sit across each other and talking to each other and telling that, oh, yes, we can do this, but we need the water, the amount of water coming. And then we have another person saying that, yes, we have this data. And that was one of the starting points of how we're seeing this change in how India is managing its water. From just looking at it from one lens, we've implemented it and not looking at it further, to a more circular approach of taking a look at end-to-end as well as where it's going to end and where is my money coming from and how I'm going to be able to sustain it. But then there's always this transition phase, right? This Ghaziabad reuse that I spoke of earlier is also in the transition phase. So there's a lot of trial and errors. We do have some industries who have taken up wholeheartedly because one, Ghaziabad, the industries in Ghaziabad, they usually use groundwater, which is having a TDS of close to 1,000, 2,000 and above sometimes. But now these industries are getting water of a TDS of 500, which basically means that there is lesser need for them to further treat this. Therefore, even though there is a cost of buying this water, which is more expensive than extracting the groundwater, but there are benefits to them in terms of the operation and maintenance cost of their treatment plants is reduced. So there will be a requirement for various strategies and action plans, and these have to be very localized. I'm come to the end of my presentation, and I would like to thank our research and implementation partners as well as our funding partners, and I look forward for any questions that you may have. Chandrasekhar, over to you.
Yeah, Thank you so much, Nathaniel. It was such a nice presentation. I am not sure people would be, most of the people are still unaware about this treated water, which India has also started reusing it. And it's a good thing it has started, and people from many places would be taking up this, and even from the academic point of view, people are unaware about the recycling of this wastewater or used water. Yeah, and the floor is open for discussion. If you have any doubts or clarifications, kindly pose your questions. I'll try to unmute you. Yeah, meanwhile, you can start asking your questions through chat box also.
I think I have a few of my colleagues also here who can also take up questions in case I am not able to answer them.
Okay.
If there are no questions, I can answer the previous questions about groundwater, how they're using like the groundwater of Australia compared to.
You can go ahead till they will ask questions. You can go ahead answering that.
So, like the Millennium Drought of Australia, right? It also gave them opportunities. Like for example, we saw a similar drought being faced by people in Chennai, which presented an opportunity to look for alternative water sources, such as desalination, which is expensive, to the safe reuse of treated water for industrial use as well as other uses as well. The Millennium Drought in Australia is a case of where, like, which is a case of where striking where the iron is hot, right? So when this Millennium Drought was happening, they brought about various different changes. So they brought in the Murray Basin plan, management plan, and with regards to groundwater specifically. So usually these agricultural zones in Australia, they have water credits, in which they are able to use, which basically mean that if I am a farmer and I have 100 water credits, but I only use 20 for my own use, I can sell these 80 credits. So if something like that comes to India, I feel that there is a question. Give an example of Pune followed by Chennai treating water but not by oceanic waters using RO process. So they are using desalination process, but using an RO for salt water, for like oceanic water, is too expensive because the TDS is way too high. So you like TDS from wastewater is just a fraction of what the TDS of water from the ocean is. So cost is the limiting factor here, Vinayji. Other than economics, the resource will be perennial, at least in drought seasons. Can you clarify, Vinayji?
You can also use your mics to pose the question.
So what I meant is, let's say Bangalore, Chennai, or any other places, definitely I agree with you treating water. In many cases, they are going for tertiary treatment, but most of the cases it is secondary treatment in most of the cases. But when you say tertiary, it's a costly process. It's a very costly process, if I'm not wrong. And in those cases, let's say when you are closer to the oceans, definitely, as you said, I will take that answer, stating that the salinity is very high. Other than the economics, are there any other options? So that's what I meant. It was a continuous question, which I typed something like that.
Okay. So to answer that, well back into
Other than the economic aspects, yes, I understand with you stating that it's economically very high, it's not so feasible. Forgetting the economics, is there any other way? Like, let's say when we distill water, also we have to heat the water so that we get the vapors, and we are using that one. Something like that. Why am I asking this one is many places in Telangana or many places in because they're using something called Kenyan water for drinking, wherein they're breaking the hydrogen and oxygen ions, etc., and that unit cost is also very high, even though it is not recommended by the doctors or anyone like that. Why not here? Why not here? Wherein certain things can be addressed other than the economics part.
Yeah. So I'll take the example of Surat, but from a different lens, right? Surat in the 90s was experiencing plague because of mismanagement of solid waste, right? Because of this mismanagement of solid waste, people started getting plague, which is unheard of, like in modern era. But then we had people come and step up. There was the municipal commissioner in the 90s of Surat, was instrumental of taking a call that no, it is my responsibility. So he was driven to ensure that this modern city of Surat should move ahead and be healthy. And they implemented a lot of programs and efforts, and we can see that in the Surat that it is today, continuously improving, right? So until and unless people face wrath or face an issue, they will not be driven to find solutions. So, which is the reason why solutions are being found when we are facing issues. Regulations and guidelines for safe reuse of treated water in India. One, Vivek Reddy ji, is this national framework, which is the key one. And secondly, there are various CPCB and Indian standards by BIS that have already been developed. So the SRTW framework does not develop new regulations, but it builds on existing regulations. How can we regulate biomagnification of contaminants and microplastics in biological food chain? There are various answers to this, Dr. Uttam Anda, but I feel that we are focusing more in a little bit too much in the downstream efforts, which is when plastic becomes waste. We are also working on a project called Innopol, which is the cooperation project to reduce plastic and chemical pollution, because plastics, to give them various properties, plasticizers and other things are added to give them various properties. And some of these plasticizers and all, they are not meant to be used for food contact plastics and all that. But since it is not regulated, right? And even the people who are making these plastic products, most of the times unaware of the chemicals that they are putting in the products. So we are currently working on a concept where we look to address upstream measures. Upstream measures, the easiest way to do this, especially in the plastic sector, is to look at these batch manufacturers. So these batch manufacturers, these batch makers, they have these chemicals which are either in powder, liquid, or pellet form, which are mixed into polymers, different polymers, to give them various properties. And some of these chemicals can be very hazardous to health. So if we are able to generate guidelines for industries, because we have seen through our research in both Gujarat and Tamil Nadu and Delhi, that the people who are actually producing these products are unaware of what chemicals are in the plastic polymers that they are using. or they choose not to because they're making profits by using a lower polymer grade. They will use these plastics, and there have been several instances where we have people who are developing food containers, going to plastic recycler who's not making recycled plastic to the grade of that has been required by FSSAI. So in fact, FSSAI has actually come up a couple of years back with regulations as to how plastics can be reused again into food contact items. I firmly believe that it requires an upstream effort rather than downstream effort. It makes no sense to treat it because it's too difficult, and prevention is always better than cure. I hope that answers your query, Dr. Tampandaji.
Yes. Any more doubts that you have? Whether they, apart from Surat and Chennai, where are these such practices where they have started reusing this?
All over India.
Okay.
Like I've just come from Haridwar, where they're reusing this water from this STP, secondary treated water from this STP. I think it's a 62 MLD plant, which is women-run, completely women-run 62 MLD, and being used to irrigate. In fact, it was one of the requirements when we were conducting these assessments and talking to various departments on how the Uttarakhand SRTW policy should look like. In agriculture, you have the Aurangabad Purple Pipe study, which is a very good case study. Bangalore is also doing some reuse, but then the response from farmers is mixed, so which is the reason why I haven't mentioned it here. The Mumbai airport, the Delhi airport is reusing a lot of treated water and saving them lakhs of rupees daily by reusing this. Like in Delhi, they reuse it for flushing, and you've seen the Delhi airport has a lot of landscaping, and all of the landscaping is being done through treated used water. There's one more question.
Yeah, you can take.
How can societies implement effective strategies integrating individual actions, technological innovations, and community-based initiatives to reduce resource consumption and waste generation, ensuring long-term environmental health, equitable resource availability for future generations? So societies, they're not like, you do not assume that they already have the technical know-how. First, there must be some hand-holding for societies. For example, we've seen in Punjab, there have been for some villages, they are actually using constructed wetlands and as well as lagoons, these retention pools, to treat this water, and they're reusing it for farming and all that. So societies can implement it if they have the technical know-how, but they definitely need hand-holding. You cannot just give them training and say, here you go, because like treatment and issues will creep up. And if issues aren't solved on time, if there isn't a person available there to help them with the issue, then there is a chance that the entire system degrades. So timeliness and the availability of technical know-how is definitely required. In fact, the Aurangabad Purple Pipes case study, we actually have the farmers paying for the water that they're buying the water. Yeah, and secondly, not just buying the water, they're also paid partially for the pipelines to supply the water to their farms as well. So a lot of things is happening. I hope that answers your question, Gaudaji. Shri. And I think that's the end of it, right, Chandrasekhar?
Yeah, I hope, because we have our next speaker. It was a nice presentation, and we from Vishweshwaraya Technological University and from participants, we thank you for such an informative session and delivering us your knowledge on treated wastewater, its reuse in various purpose. Thank you so much, Nathaniel, and we hope that you will be supporting us in the future days to come in the same way.
For sure. Look forward for future collaboration, Chandrasekhar.
Sure. Thank you so much.
All the best for the rest of the competitions and the next speaker.
Yes. Thank you. We have the next speaker, Shri Gopalkrishna Sanatangi, sir. Before you are there, sir?
Sir is there, sir.
Yeah. Good evening.
Yes, sir. Give me 2 minutes, sir. I'll just make some announcement before we start. I have made you as a co-host. You can start presenting your slides if it is there.
Okay.
Yeah. Dear audience, kindly assure that the quiz that is going to happen, it is starting at 6:30. So at no other time it will start. People are calling me, people are messaging me. Unless the sessions are over, you will not be allowed to start the quiz. I've been telling it through WhatsApp also, and to many people. When it is starting at 6:30, it will start at 6:30 and it will close after 45 minutes. So if there is any internet issues or connectivity issues, it is sole responsibility of the participants. As it is conducted by Atal Academy of AICTE, it is not being conducted from our side. So please be careful, ensure that you have a good connectivity and complete the submission within the stipulated time. Your attendance is also very much mandatory during the valedictory session. You have to be there in the valedictory session, which might take hardly 15 to 20 minutes, where we will be sharing the feedback from the participant side and small information about the session. So the attendance during the valedictory is also important as per AICTE. You have to be there in all the sessions. Feedback is already started. You can give us feedback through your Atal portal login. On the left hand side, when you see the feedback, you can get the feedback right now or any time you can give the feedback. There is no much problem in that. The third, one more announcement is the email ID of all the speakers will be shared to you after the completion, either through your Gmail or through this WhatsApp group. Right. Thank you so much for your patience hearing. I shall now take up the next session, which would be the last session of this 6 days online FDP program. Yes, sir. Gopalkrishna, sir. We shall start. Yes. I'll just introduce you, sir, before I start.
Okay. Good evening. Am I audible?
Yes, sir. You are audible, sir. You are audible.
Okay. Good evening. And last session is always is a big challenge for a speaker. So today's my discussion is on industrial waste management. And as we know, it is so complex and it depends on the type of raw materials used and the chemical composition and the wastewater. It is very complex. So I'm trying to address few issues, few points, and I'll share all the presentation to you, sir. So just, I hope I am audible, no?
You are audible, sir, but can you present it from your side or?
I'm just trying to share it. Okay.
Right. Meanwhile, I'll just introduce you to the audience.
Okay. Okay. Just a minute.
Shri Gopalkrishna B. Santangi sir is from Karnataka State Pollution Control Board, where he has joined KSPCB in 1992. Worked as environmental officer at Karwar, Shivamogga, Ballari, Belagavi, and Bidar. Now he is working as a senior environmental officer at Belagavi. He has completed his MSc from Karnataka University, Dharwad, post-graduation certificate course in sustainable engineering and smart cities from IISc Bangalore. He is a lead environmental auditor. He has also completed lead environmental auditor course. He has guided many MTech students on treatment of effluent from dairy industries. He has carried out ETP evaluation studies for sugar and distillery plants, ETP treatment and recycling studies for gene washing units, technical studies for pharmaceutical units and tire pyrolysis plants. He has attended many national level workshops in the field of environmental conservation. He has stopped iron ore movement during monsoon period. Technical report was, even he has submitted the technical report to the district administration. He has implemented ETPs in 18 pharma and tire pyrolysis plants, implementing gas holders for tire pyrolysis units and utilizing gas as a fuel, which was generated from the process. He received appreciation certificate from Maritime Federation, Washington, USA for beach cleaning program also. He has initiated Green School program, which is well known as Parisara Mitra Shala. So that was a brief introduction about the speaker, and we welcome you, sir, for the session.
Okay, thank you.
Share the slides, sir. If it is
yeah, I'm sharing. Is it visible?
No, sir, it is not.
A minute. Now, is it visible?
Yes, sir. It is visible, sir. You can make it as a full screen, sir, a slideshow.
Okay,
yes.
Okay.
Yes, sir. It is now.
Yeah, it is visible, no?
Yes.
Okay.
Sir.
Good evening. Yeah. Good evening, all. So, whatever that wastewater treatment, what we are designing, generally it is in the interest of the surface water and environment. So, to understand what is water, what is wholesome water, it should be free from pathogenic agents, harmful chemical substances, color, odor, taste. It should be pleasant taste and usable for domestic purpose. We all know it. So how the natural impurities occur? Their impurities either in the form of dissolved impurities or suspended impurities. And in dissolves, it is in solids or gases, and suspended inorganic or organic. This presentation I'll share you. I'm going to just briefly, I'll go through this. So what are man-made impurities? There are drainage sewage, industrial, trade waste, agriculture pollutants, physical pollutants, and water-related diseases. We all know waterborne diseases caused by ingestion of water contaminated by human beings or animal feces or urine containing pathogenic bacteria. And diseases, we know it is a cholera, typhoid, amoebic and bacillary dysentery, and etc. So why I'm telling all these things is because while designing any effluent treatment plant, we should keep all these things in our mind, and it should design. Earlier, it was going for a irrigation purpose, but now, due to scarcity of land, so government is suggesting to go for a zero liquid discharge, and water is not allowed to be discharged into any surface water or a river. But still, during rainy season, there is a chance that this effluent is likely to go into our surface water and eventually reach a river and come back to us in the form of drinking water. Though we have a treatment for drinking water, but most of the components, they are not addressed there. They are only BOD, COD, or some pathogens that have been removed. But the chemicals which are present, they are not addressed. And as per Central Pollution Control Board, they have classified water into A, B, C, D, and E. And very unfortunate to tell that there is no river or surface water body except Ganga or few rivers at their origin. They meet this class A water. That is, you can drink without any treatment. And most of the water either they fall in B, and in Karnataka they fall under C category. Means they are contaminated with the BOD, organic load, and fecal coliforms also. So this is a so water actually. What type of water is required for drinking water specifications? So I'm just sharing. This is available in BIS. You can go through this. These are the different quality of water, that is parameters should be there. It should comply to all these parameters. So this is available in our BIS standards. It is available on website as well. So I don't want to go much deeper into this. So I would like to mention what are the water quality standards. So this is a water quality standard which we have to meet, that is the BIS standards, desirable limits and permissible limits, and other things. So if you see odor is agreeable, then pH acceptable is 6.5 to 8.5. That is a permissible limit. And if it is more, it has given what will be the effect of it, risk or effects, like it will be corrosion, metallic taste, and pH bitter, soda taste, and it can cause a health effect as well. So other parameters are like total dissolved solids, that is in a dissolved, that is a permissible, acceptable is 500, permissible is 2000 milligrams per liter. And I'll just go through few slides, not all of them. And turbidity, which is acceptable unit is 1 NTU and permissible limit is 5 NTU. So based on these parameters, we have to design the effluent treatment plant. So unless we don't know these things, we required water quality, where this treated effluent is going to finally join. So it is very difficult for to design in complete form the effluent treatment plant. So this is aluminum, and the acceptable limit is 0.03 milligrams per liter, permissible is 0.02 milligram per liter. And high risk associated with a dialysis patient, especially it causes a problem to kidney patients. And ammonia, as we know, acceptable is 0.5 and permissible is limit is no relaxation. So it should not be more than 0.5. And if the risk or effects is none proposed for human but toxic for aquatic life. So this is from Bureau of Indian Standards. So these are the different metals. They are telling about barium, what is acceptable and what is permissible. So these are the things. Just I will not go through all the parameters, like one or two more I will just discuss with you. Manganese, acceptable is 0.1 milligrams per liter, permissible limit is 0.3 milligram per liter. And risk is it causes health issues. It is already mentioned here. And one more is sulfate, which is permissible is 400. And nitrate. Nitrate is very important. This indicates the organic pollution, sewage contamination. Acceptable is 45. And permissible, there is no relaxation. So this is usually causes blue baby disease in infants. And sources are livestock facilities, septic systems, and etc. So these are the few things I just wanted to bring to your information. And second thing is the National Ambient Air Quality Standards. Because unless we know all these standards, the designing of a pollution control facility will not be complete. Suppose if we design something which doesn't meet to the required standards of either drinking water quality or river water quality, then that treatment plant is not in complete form. So these are the National Ambient Air Quality Standards. We all know that sulfur dioxide is, they have made it into 3 categories, residential industrial area, it should be not more than 50 micrograms per meter cube. And nitrogen dioxide, sorry, and that is 40. Particulate matter, that is a 60, and PM 2.5, which is more dangerous, it should not cross more than 40, because this is particle size is 2.5 micron, which will directly go into our lungs and cause a breathing problem and lung related diseases. So these are the few things I just wanted to share with you. Okay. Now, elements of water, as I just discussed, elements of life is water, earth, air, fire, and sky. And the water spread in the entire world is 97% is in ocean form, and 3% is fresh water. And out of 3%, 28% is available in Asia, 45% in America, 16% in Africa. So before designing any effluent treatment plant, we need to know the characteristics of wastewater. Unless we don't know the characterization or fingerprint analysis of the wastewater, we cannot design the effluent treatment plant or a treatment scheme. The basic things what we look into while designing any effluent treatment plant is physical characteristics such as solids, total suspended solids, that is in the form of then total dissolved solids, and volatile suspended solids, turbidity, then color, absorption transmittance, temperature, electrical conductivity. This shows the chemical composition and hardness of the water. And next is chemical characteristics like pH, chlorides, alkalinity, and nitrogen and phosphorus, metallic constituents like cadmium, chromium, copper. This heavy metal treatment requires a different type of treatment. It requires a chemical treatment like a precipitation. You have to remove all these heavy metals and take the other effluent for the treatment. So while designing any effluent treatment plant, we should understand what is the water balance, how much water is consumed for different usages, and how much is discharged. And similarly, the materials also, raw material, what is the raw material they are consuming, what is the product they are manufacturing, what is the byproduct is generated, and what is the waste. But nowadays nothing is a waste. Everything can be recycled. That is a new concept has come that I'll be discussing with you in coming slides. So wastewater treatment, the disposal or reuse processes used, the phase separation, oxidation, polishing, then sewage treatment plants, as my other speaker has already spoken to you in detail, agriculture wastewater treatment plants, leachate treatment plants, and etc. So wastewater treatment plant, as we all know, it has to, that wastewater has to meet to the required norms wherever it is discharged. So generally nowadays it is standards have been so stringent. Earlier BOD was allowed up to 100, then it came down to 30. Now it is a 10. So coming since because of the land scarcity and entire water has got polluted, it is not meeting the required criteria. So standards have been revised, have been made more stringent. So disposal, although disposal or reuse occurs after treatment, it must be considered first, since disposal or reuse are objective of wastewater treatment. So the main focus is given only on reuse options, and if it is disposed, that has to be used for certain usually it is not allowed to discharge into any water body. It is allowed for irrigation purpose and other secondary uses. So what are the processes used? Is the phase separations, sedimentation, filtration, oxidation, biochemical oxidation, chemical oxidation, and polishing. So we all know what is a phase separation. It is a transfer impurities into non-aqueous phase. Phase separation may occur at intermediate points in a treatment sequence to remove solids generated during oxidation or polishing. Grease and oil may be recovered for fuel or saponifications. So sometimes some waste, whatever is in, especially in the oil industry, that waste contains some oil traces of oil, which is further used in the manufacturing of soaps and in the by saponification process. So sedimentation, again, it is a settlement. It is a physical settling of the solids like stones, then other things. By gravity, this is a by gravity separations. And filtration, suspended solids and colloidal suspensions of fine solids may generally follow some form of coagulation, be removed by filtration. It is, they will add some coagulants, then it is filtered. So this is how all these things are separated out. Then oxidation, as we all know, biochemical oxygen demand of wastewater may reduce the toxicity of some impurities. So it requires secondary treatment like aeration and other things, which will remove the biochemical oxygen demand. So I don't want to speak much on the sewage treatment plant, which is already discussed. Secondary treatment by biochemical oxidation of dissolved and colloidal organic compounds is widely used in sewage treatment plant and is applicable to some agricultural and industrial wastewater too. Chemical oxidation, chemical that is including electrochemical oxidation is used to remove some persistent organic pollutants, which are very dangerous, POPs. They can cause a serious threat to our health. And concentration remaining after biochemical oxidation, disinfection by chemical oxidation kills bacteria and microbial pathogens by adding ozone, chlorine, or hypochlorite treatment. Then polishing. So what are the wastewater treatment plants? There is a sewage treatment plants, tertiary treatment plants, industrial wastewater treatment plants, agriculture wastewater treatment plants, and leachate treatment plants. The tertiary treatment plants, as we know, it involves microfiltration and by synthetic membranes. Nitrates can be removed from wastewater by natural processes in wetlands, but also via microbial denitrification. As we know, I think my other colleague, my other speaker might have spoken to you about denitrification. Ozone wastewater treatment is also growing in popularity and requires the use of ozone generator, which decontaminates the water as ozone bubbles percolates through tank. The latest, the very promising technology is the use of aerobic granulation. So industrial wastewater treatment plants. Disposal of wastewater from an industrial plant is difficult and costly problem. Most petroleum refineries, chemical and petrochemical plants have on-site facility to treat their wastewater, and most of them, they are looking for a recycling. That nowadays, a pollution control board is has made it mandatory to adopt ZLD, that is a zero liquid discharge concept. So everything has to be reused for the different industrial application or for irrigation purpose. So this is a simple flow, that pictorial image, how this nitrogen cycle, it is a nitrogen cycle, how nitrogen is decomposed and made into again goes back into atmosphere in the form of nitrogen through bacterial activity like nitrifying bacteria and nitrogen fixing bacteria and etc. So these are leachate treatment plant. As we know, leachate treatment plants are used to treat leachate from landfills. So wherever there is a garbage, that a solid waste disposal site, there is a leachate is generated. That is usually treated by ultrafiltration, biological treatment, mechanical treatment by ultrafiltration, and carbon filtration. So this is a leachate tank where leachate is generated in solid waste dump site, and this wastewater is treated and used for secondary uses like in composting or for gardening purpose. So effluent treatment plants or ETPs are used by leading companies in the chemical industry to purify water and remove any toxic and non-toxic materials or chemicals from it. These plants are used by all companies for environment protection. So types of treatment, as I already told, biological is anaerobic treatment, which involves UASB. Then aerobic treatment, which involves activated sludge process, SBR and ABBR. Non-biological treatments are whenever there is any chemical contamination. So it has to be done by precipitation, electrocoagulation, RO, UV method, evaporation, centrifugations, and multiple effect evaporators and various other measures. So biological treatment, as I said, anaerobic, that is digesters are used where the COD is more than 5,000. That is this anaerobic, in anaerobic form, fermentation is taking place and that is treated. And that further that waste is taken into aerobic treatment plant in a aeration tank. So this is activated sludge process, which we call two-stage aeration, followed by aeration, followed by settling, then again aeration. So this is an activated sludge process, which is generally practiced in industries. So activated sludge process is a flow diagram, bar screen, where coarse materials are removed in collection tank. Then where in collection tank it is homogenized and taken into aeration tank, and whatever is settled, solids are settled, it is settled in settling tank, and solids are again taken it back to aeration for microbial development, and further from settling tank, which we generally call clarifier, it goes into filter feed tank, then PSF, pressure sand filter, then activated carbon filter. So there are different types of treatment systems. What we know, SBR means sequential batch reactor. In this tank, aeration tank and settling tank are the common. It consumes very small area, and usually this is installed in apartments where area is not available much. So this is a flow diagram of SBR process: bar screen, collection tank, SBR tank, then decant tank, and further this water can be used for different purposes. So design of ETP and size of ETP depends on quantity and quality of industries discharging effluent, land availability, monetary consideration for construction, operation and maintenance, flow rate, type of treatment to be used. So this is just a photograph showing what was quality before treatment and what is the quality after treatment. So all the solids have been settled. So it has to be decanted. The clear water can be used for different purposes. So this is a typical flow chart for sugar effluent, where oil is removed and is taken into collection tank, neutralization tank, where pH adjustment is done. Then it goes into primary aeration tank. Then from there it comes to primary clarifier or settling tank number 1. Then it goes to secondary aeration tank. Then from there it goes into secondary clarifier, and finally it will be treated in pressure sand filter and activated sand filter, carbon filter it is, sorry. So this is a typical sugar activated sludge process flow diagram. I don't want to go into it. And these are the photographs of surface aerators in aeration tank. The surface aerators where you can see it in sugar factories and most of the industries. And this is neutralization tank. This is clarifier or settling tank, you can say. Then clarifier, where is separated by gravity method. And whatever sludge is generated, it is stored here, and water is removed, and the dried sludge can be used for agriculture purpose, and depending on the type of waste sludge it is. If it is chemical sludge generated from chemical industry, it will be classified as a hazardous waste, which has to be given to TSDF, that is a solid waste, hazardous solid waste disposal facility. So these are the different photographs of RO and DM plants. Biological treatment, surface aerators I just showed you, and precipitation process followed by biological treatment, and ETP precipitation process. Where there is a chemical effluent, you have to go for a precipitation by adding some alum and other things, which will settle down all the solids, and that can be separated out. So this is packaged plant STP, small STP, which is generally used in apartments and small facilities. This is MBBR aeration tank. This is nowadays it is being used everywhere. So these are the membrane filtration modules which are used for filtration purpose. So how to selection of technology based on effluent quality for ATP? If it is having a low TDS, low dissolved solids, and low BOD, low organic, we can go for a chemical treatment. Low TDS, high BOD or organic effluent, we can go for anaerobic plus aerobic treatment. Low TDS, high COD, high organic, we have to go for chemical oxidation and go for a chemical and biological treatment. So it depends on the type of effluent waste. We have to decide what type of treatment scheme we have to sequence we have to adopt. So sustainability criteria for assessment of ATP technology. Performance expressed in removal of BOD, COD, heavy metals, organic, micropollutants, pathogens, and nutrients. Adaptability, possibility for implementation on different scales, increasing, decreasing capacity, anticipated changes in legislation, etc. Durability of ATP, which has to lifetime of installation. Flexibility, that is very important. Sensitive for process in terms of toxic substance, shock loads, seasonal effects, sometimes during rainy season or during high temperature, or there is any shock load. Suddenly it will be designed for some quantity, but suddenly there will be a discharge of more quantity by many process disturbances. So it should be you should have a flexibility to manage this situations as well. Maintenance, frequency, cost, and time needed, reliability, economic, it is affordability, cost effective, labor, willingness to pay. Then resource utilization is energy. It should consume less energy, and so that has sustainable energy sources can be explored. And functional land area required, nutrients required, and organic matter. And social also, if it is discharged outside, that also counts very much important, because if there is any residential area or any sensitive area, so we have to decide where this treated effluent has to be discharged, or it has to be, generally it is recommended to reuse for in the industrial purpose only. So this is a wastewater reuse basic diagram of integrated membrane system for treatment and reuse. So whatever effluent is coming, that sewage or factory, wastewater, it goes into MBR, activated sludge, or micro filtration, ultrafiltration. Then it goes into reverse osmosis and reuse. That is taken back. Usually this treated wastewater is used in the boiler feed or process water or cooling purpose. This is inlet quality, effluent quality, and discharge standard for CETP. So just I want to add one more thing. Nowadays, for all industries, small industries who cannot adopt or afford costly effluent treatment plants, the government has come up with a scheme of common effluent treatment plants, and many private people, they have put up common effluent treatment plant, and they are collecting effluent from all the industries, small industries up to medium scale industries, and treating based on its chemical, its quality, effluent quality, that is treated in their common effluent treatment plant. These are the inlet effluent quality required, and these are on the other side, we are given discharge effluent standards, and that is given here. So wastewater treatment levels and processes, preliminary removal of large solids such as rags, sticks, grit, and etc. There is a physical process. Primary is a physical and chemical process. Secondary is biological and chemical process. Then tertiary is physical, chemical, and biological. All three are involved. So industrial effluent, just I showed you this flow diagram. Industrial effluent, it goes into screen chamber, and then where all the coarse material are screened out. Then grit chamber, all the settleable material, it gets settled. Then it goes into equalization. This is to avoid any shock load on the aeration system. Equalization tank is taken, then primary sedimentation. These things we can modify depending on the type of effluent. Then it goes into aeration tank. From aeration tank, it goes into secondary clarifier and treated effluent for different industrial. So this is zero liquid discharge in distillery. You must be knowing that there are many distillery units. That I will discuss you later in, I have got one case study I'll present before you. And these are the different types of treatment used in different type of industries: knitting mill, printing and dyeing mill, then printing and dyeing mill in Beijing, and so many. What is the scheme they are following? So friends, I will now I will take you into the CTP. Just I want to discuss with you about just a minute. Okay. Just brief presentation I would like to make on common effluent treatment plants. This was made by my colleague Dr. Ravi. He is no more. So public good non. I just skip all these things. So treatment plant sequence in common effluent treatment plant is it is very clearly shown here, like primary treatment where bar screen and grid chamber, settling tank. In secondary it goes into aeration tank, and from aeration tank all the solids it passes through one more clarifier, that is settling tank. The solids will get settled here and clear water comes here, and this is they will do some disinfection by chlorine disinfection or ozone, and again the sludge will come back either back to the aeration tank because it needs some microbial culture, and excess will go to sludge digester, and from there it goes to landfill. So water pollution control theory, philosophy: raw water source, then raw water treatment, wastewater, then again it is reused. So common effluent treatment plants evaluation: industrialization is seriously impacted the global environment. Pollution caused by small-scale industries is a major environmental issue. Nowadays, if you see the sewage, what is generated in urban area, earlier it was only a sewage that was organic load, but nowadays if you see, it contains all the chemicals because of small-scale industries. They are discharging, dyeing industries are there. Even in hotels, hospitals. Recently, there was a characterization of effluent generated from hospitals also, because they are using a lot of chemicals and radioactive materials for a treatment, and this all goes into wastewater, and these are not treated effectively, and they goes into our water body. So how the collecting the CETP concept is, it collects effluent from all the small industries and they treat it, and again this treated effluent is given for a secondary uses for industrial purpose or a construction purpose. And we all know in Bangalore that sewage treatment plants, the treated sewage is pumped to nearby talukas like Kolar and Chikkaballapur, where they are used in tanks, and further that is used for different purposes. The concepts of CETPs: achieve end of pipe treatment of wastewater to avail the benefit of scale of operation, reduces number of discharge points in an industrial area, better enforcement by environmental regulatory agencies, potential benefits in terms of pollution reduction, environmental improvements. So objective is reduce treatment costs for individual units while protecting the environment. Achieve economies of scale in wastewater treatment, thereby reducing cost of pollution abatement for individual industry. Minimize lack of technical assistance and trained personnel. Solve the problem of lack of space, as centralized facility can be planned to ensure adequate space. Reduce problems for monitoring. Organized the disposal of treated wastewater and sludge. Improving recycling and adopting cleaner technologies. So CTPs can be categorized as homogeneous or heterogeneous. And homogeneous, where similar type of industries are operating, like some dyeing industries may be there, or tanneries in Tamil Nadu, paper industry. But whereas heterogeneous will be a different type of industry, and this is very challenging for a CTP operator because it contains different type of effluent and different chemicals. So it has to be brought to the common quality and further taken for a treatment. So design criteria, quality, flow rate, effluent standard required by the CTP, possibility of recycle, reuse of treated wastewater, availability of land, manpower, and etc. Then second is combined effluent treatment plant, that is can be changed to combined effluent treatment plant when it collects sewage from surrounding localities and treat it with industrial wastewater. So this is a mixture of sewage and industrial wastewater. That is also possibility is done. So technical aspects of CTP, basic information about individual unit, their raw materials, products, treatment if any, quality and quantity of wastewater generation, scope for waste minimization, and collection and conveyance is also very challenging. And pre-treatment, individual units should have a pre-treatment system in their plant so that it can be compatible in common effluent treatment plant. Otherwise, pre-treatment is again a challenging for a common effluent treatment plant. Usually, we recommend for a pre-treatment in their own in-house, in their own individual respective plants and disposal. So advanced wastewater treatment, again, these are the different types of treatment that is adopted. ISBR, MBR, moving MBBR, wet or dry air oxidation, electrocoagulation, then multiple effective operation, MVRs are also available. So membrane filtration, RO systems, ion exchange, activated carbon, multiple effective operator with agitated thin dryer film, thermal evaporation, forced evaporation, and vacuum evaporation. So selection of waste technology, wastewater technology, again, as I discussed, depends on the type of effluent. The financial aspects, I don't want to go into it. And financial support, the government, central government, there is a 25% grant is there for CTP, and the state government gives 25%, and the contribution from the small scale industries. So these are the different influent quality of CTP. It is available in the MOF website, and treated water standards, it is given. Friends, I would like to discuss about the solid waste, which is hazardous waste. As we discussed in industry, it generates a lot of solid waste, and this solid waste is categorized as a hazardous and non-hazardous solid waste. And non-hazardous, that is other waste, can be used for different purposes, like non-hazardous solid waste is either this one, a paper or ash. So that can be used for different activity. But the challenge here is hazardous waste. So what is hazardous waste? A waste that contain any of the following characteristics. It should be flammable, corrosive, reactive, it should be toxic, poisonous, carcinogenic, and radioactive mixed waste. There is a schedule of type of industry, what type of hazardous waste it is going to generate. There is a rule for hazardous waste management, as we seeing through this, the evolution of hazardous waste management rules and other things. Okay, just a minute. Okay. The first time, hello?
Yes, sir. Yes, sir. It is visible.
I'm audible, no?
Yeah. Yes, sir. Yes, sir. Yes, sir.
Okay, okay. So for the first time, rules have been made to distinguish between hazardous waste and other waste. So other waste include waste tire, paper waste, metal scrap, used electronic items, and etc. So waste management hierarchy in sequence of priority of prevention minimization, reuse, recycling, recovery, co-processing, and safe disposal has been incorporated. So you must be knowing most of these hazardous waste, whatever earlier it was a linear economy where you produce the product and forget about the byproducts or waste. But nowadays, everything is a circular economy. Whatever waste is generated, that is either used for a secondary purposes or for a co-processing. Co-processing is nothing but if any waste is having a calorific value more than 3,500, that can be co-processed in the kiln or in the cement industry and used as a fuel. So this hazardous waste is used as a fuel in cement industry, and that reduces a lot of consumption of coal. So the approval for co-processing and hazardous waste to recover energy has been streamlined. So on priority basis, the trial basis, earlier there was a trial base, compulsory trial base permission was required, but now it is not required. So new rules not applicable, like yeah, okay. Okay, the utilization of hazardous waste as a resource or after pre-processing, because this hazardous waste is collected from different industries, and their CV is they're mixed in such a manner that by chemical treatment they should be compatible, and also their CV should be more than 3,000, and that waste is given for a co-processing purpose. So utilization of hazardous waste and other waste, no trial runs, as I told you, no trial runs is required. And there is a standard operating procedures. Oh, I'll go to the landfill sites. Okay, yeah. Here is a co-processing in cement industries, cement kilns, as I told you. More than 90 co-processing trials were made in India, and all the waste, hazardous waste generated from pharma, chemical, automobile, they are used and used as a fuel in co-processing in cement industries. So this has reduced a lot of hazardous waste which was earlier going into landfill. Co-processing business model is operating for past 15 years in India. Volumes are increasing year by year. So there is a national task force on co-processing has evaluated and concurred with the co-processing business model of hazardous waste, hazardous and other waste, as well as for RDF from municipal solid waste. So whatever burning component, that is refuse derived fuel, what we call in garbage, that is municipal solid waste, that is also used as a fuel in cement industry. So if you nowadays, if you are seeing the most of the plastic and other whatever is which has got a calorific value, it is going to cement industry for a co-processing purpose. Even in Belgavi also, nearly around 250 tons more than that. They have, I may be wrong in the numbers, but that has been given to cement industry in nearby cement industry to use as a RDF, as a fuel. So that will reduce the burden on the utilization of coal, which will generate, this will reduce the generation of emissions what was about to generate from the using coal. So in Tamil Nadu, the Telangana State Pollution Control Board, they have permitted 7 pre-processing facilities. In Karnataka also few facilities are there, and they are in Andhra, they are pre-processing around 3 lakh tons per annum. The total quantity of hazardous waste sent to co-processing to cement industries, both within state and outside state, is I'm giving you the status of Telangana state, is around 1,20,000 tons has been given to industry. So some thermal substitution rate in Indian cement industry by use of alternate fuel was in the range of 0.5 to 1% in 2016, and the target has been set to 20% by 2025, by this year. And this can reduced by 20 million tons per annum. Fossil fuel requirement can be reduced to this much, 20 million tons per annum. So energy recovery is 80% and 100% material recovery through co-processing in cement kilns, compared to zero material recovery and less than 30% energy recovery in waste to energy plant. So nowadays we are the government is encouraging co-processing for utilizing hazardous waste as well as other municipal solid waste as well. So this is a waste tire regime. I don't want to go into this, so I'll just go through. And waste oil, whatever is generated in the industry, that is given for a waste oil recovery facilities have come. They will remove the impurities, and this used oil is again sold in the market. So this is how the waste is what we call a circular economy. It is reused. So I will skip all these things. So this is hazardous waste management, secure landfill, incinerator, and TSDF. I've taken this presentation from Ramki. They are operating in Hyderabad. So just suppose if the waste is just left as it is a pictorial representation how this hazardous waste can contaminate surface water. So this has to be properly landfilled with all precautions. So secured landfill, this is called a secured landfill. So whatever solid waste, the hazardous waste is there, that is stored, and there is a provision is made to collect leachate and also the gas. And that will be, before putting it into landfill, it is first is stabilized. Only after stabilized, it can be put into landfill site. What is a landfill? A containment system which separates the waste from surrounding environment. Objective to mitigate the migration of leachate and minimize emissions. And concept is place the waste in isolation from the environment. So what are the criteria while selecting this facility, landfill site? It should be accessibility, receptor related, socio-economic, waste generation related, and geological. And it should be away from water body, pond, lake, and it should not be a floodplain. It should be away from habitation and highways. These are the criteria which are given for while identifying that facility. And approach is, again, as I told, it should be away from thickly populated area, low population, low alternate land use. That is usually it is recommended in a barren land, not in fertile land. So this presentation is available. I can share with you. Components of landfill: the base liner systems, leachate collection system, gas collection system, final cover, and surface water drainage system, environmental monitoring system, and closure and post closure. That is very important. Once that is filled, that has to be closed, stabilized, and after post closure also continuous monitoring has to be carried out to see whether there is any groundwater contamination or leachate generation or any gas emissions. That has to be regularly checked. And these are the composite liner system, how the landfill site will have liners. This is a waste, and below it is a primary leachate collection drain. Then there is a geomembrane followed by compact clay membrane and secondary leachate collection system, and again a geomembrane, compacted clay membrane, and subsoil. This is how the landfill site has to be. So HDP liner systems are HDP liners which prevent preventive membrane, impervious, extremely low permeability. So these are the different properties they should have. That has to be utilized. So this is a clay liner, how this is during construction phase. These photographs have been taken. Clay is 15%, more than 15%. Silt, gravel, then plasticity, and so many other factors are considered. And this is a HDP lining. Once that clay is put, then this HDP lining is spread over the landfill site, and over this, the hazardous waste is dumped, disposed. So leachate collection, moisture, rainfall, leachate collection facility has to be created, and this leachate has to be properly treated and reused for the different purposes. So this is a leachate collection sump, is a design. how the leachate, whatever is generated, is collected and taken back for a treatment plant. So this is leachate collection sumps, drainage media, and landfill effective design. So here we can see the gas collection pipe. Then over this vegetation is grown. Is a small herbs they grow, not a big tree, because it will big trees will penetrate its roots into the landfill site. So small shrubs are grown, and this is how typical on landfill site, hazardous waste landfill site, cross section of hazardous waste landfill site. So incinerator, as I told you, there are some incinerators. Some hazardous waste has a calorific value. It has to be incinerated. There are three types of hazardous waste. One is recyclable, one is incinerable, and one is landfillable. So just now, till now, I discussed about landfillable. Now it is a incinerable waste. So substances having flash point less than 60 degrees, substances having more than 3000 calories of calorific value, and degradable organics and non-degradable organics. So what is the purpose of incineration? That whatever that hazardous waste contents are there, they have to be converted properly by thermal oxidation. Like carbon, it has to be converted to carbon monoxide, carbon dioxide, and hydrogen, water, oxygen, and chlorides, then nitrogen, sulfur, phosphor. So this is an effective way of incineration. If the products are not completely incinerated, not completely burned, it will end up in the formation of harmful pollutants like carbon monoxide, nitric acid, sulfuric acids, and if chlorine is not properly incinerated, it will end up in formation of dioxins, furans, and etc. So what is the key parameter for incineration? Incinerator is time, temperature, turbulence, gas cleaning system. So liquid lances feeding. Sometimes liquid hazardous waste will also come. That has to be, they should have a proper feeding facility, and a rotary kiln is required for incineration. Then secondary combustion chamber, and ash removal chamber, and gas cleaning. That is very much important. Like pollution, that is a pollution control facility. This is a typical conceptual plan of incinerator. On left side, you can see the charging hood here, and this is a rotary kiln, and it's burnt, and this is a secondary chamber. And further, it goes into the spray dryer, whatever gases are there, and this cyclone is there, that whatever particles are there, it will get collected. Further, it goes into Venturi scrubber. Whatever gas is there, it is scrubbed and goes into back filter. Any particles are there, it is collected here, and finally goes into packed bed scrubber, which will absorb any VOCs or any other chemicals. And finally, it goes in outside through chimney. And chimney is designed in such a way that the emission should go at a farther distance. And they calculate the ground level concentration maximum, how much it can achieve, it can go. And based on that, they will arrive to conclusion about making the chimney height. This is a common hazardous waste incineration system. This is one more photograph. And this is a schematic how the waste is fed. And this is a multi-cyclone, as I was telling, whatever dust is generated, that is collected here from the incinerator. And this is a bag filter. It will have a bags inside. It will collect all the particles, whatever is generated. And this is a scrubber system where liquid, any gases are there. It will pass liquid water or some absorbing solution will be passed, and that all the gases will be absorbed here, and clean air will go through the chimney. So these are the incinerator parameters are rotary kiln. It runs at the temperature of 850 to plus or minus 550 degrees, that is 800 to 900 degrees. And these are the different operational parameters they should maintain. And it should be totally a PLC control system, and everything is automatic. So how this TSDF operation is done? this hazardous waste generated from the industry is collected. There is a protocol, whatever is there, that has to go through the system of manifest. We have a e-manifest, that is electronic manifest, where he has to enter whatever type of waste he is generating online, and the receiver has to accept it, and that will go to the receiving, that is TSDF plant. So before accepting the waste, they will do comprehensive analysis, physical analysis. Then they will do a fingerprint analysis also. And because there are different type of solid waste are coming here, so that has to be made compatible with each other before going into landfill or hazardous sorry, for co-processing or pre-processing. They should have a laboratory also, and waste acceptance criteria, it is there. Leachate, they will do TCLP test, and this leachate should not contain more than the permissible concentration of phenols, arsenic, lead, cadmium, chromium, and etc. So landfillable waste, which are the landfillable waste? ATP sludge, salts and soluble substances, spent catalyst, contaminated glass wool, air pollution control dust, incineration ash, metal bearing waste, cyanide waste, and etc. So they have to get a registration from transport department while transporting this hazardous waste. So these are the manifests they should maintain. Now it is all e-manifest is followed. So this is a TREM card. These are the different how it is stored. Hazardous waste is received, then this is a landfillable, and these are the different photographs. So summary is reduce, reuse, recycle, remain high priority in waste management. However, waste remains, hence bury, burn. So if even after reduce, reuse and recycle, if waste remains, it has to come to landfill site or for incineration. Then hazardous waste have been matter of great concern globally, with large issues like Minamata Bay incident, PCBs in Mediterranean Sea, UCIL, and others. Both landfills and incinerators are subject to global criticism on following aspects. Landfills leak. Landfills are designed to action leakage rates. Incinerators have harsh emissions like dioxins, furans, and other obnoxious emissions. However, globally, these are the technologies that remain. So this is a brief thing I explained. So one more slide is there, one more presentation. This is a typical case history, you can say. And just a brief presentation I'll make on this. Few slides. So this is a public hearing. Recently it happened here in Belgaum. So I want to show you what is a public hearing process. Any project which are very significant from pollution, they have been listed. They have to obtain environment clearance certificate from either from Ministry of Environment and Forest, Government of India, or from state government. So this is a sugar factory, and they want to go for an expansion of sugar factory and establishment of distillery. So this attracts a environment clearance, and before taking environment clearance, it is a must that the local stakeholders, the public, everyone has to be informed about this project, and what are the consequences, what are the pollution things in this. Everything has to be brought into their notice, and we should also tell them what are the pollution control measures adopted here, and they should take their opinion. So this is a project site at Bailhongal, that is Saudati Taluk, Murkumbi. So I don't want to go into this. So this is a proposed expansion is from 4,900 to TCD to 15,000 TCD. That is a tons of crushing per day. That is a sugarcane, and they want to go for a cogen plant, that is a power generation by using gas, whatever is generated, to make power of 80 megawatt, and establishing 800 KLPD distillery by using C and B heavy molasses, cane juice, and grain. Earlier, usually it was from the distillery, it was run by a molasses generated from the sugar factory. But nowadays, directly making, instead of making sugar, Directly sugar cane juice can be used for manufacturing ethanol. Recently, that ethanol blending program has been encouraged in India, which there's an ethanol blending in petrol. Up to 20% they are allowing to blend it. So that has given a good potential and for distillery units, and also less relying on the import of oil. So this is existing industry setup, sugar factory, and distillery is 100% biofuel ethanol manufacturing and participation in EBP, as I told you, ethanol blending program. 100% fresh water saving. That is directly whatever cane juice is there, it contains moisture content, the same moisture and water is used in the process. And grain is used, which will consume again less water. So even importance is given for a water consumption as well. Once the water consumption has come down, and naturally the discharge of wastewater will also come down. So this is a general process, how the sugar factory, the process, how it is. Whatever after crushing, whatever bagasse is coming, that is given to boiler, and that is given to turbine, and they are generating the power. And after juice extraction, whatever press mud is coming, it is sold. But nowadays, this press mud is also used for making compressed biogas. Most of the units are already established. And whatever molasses, after taking out the sugar, the molasses, whatever it comes, it is taken to the distillery plant. Is a fermentation. Either you can directly take a juice or a molasses, and fermentation, distillation, and after distillation, whatever waste is coming after taking out of ethyl alcohol, whatever is coming, that is called a spent wash. That is fed into multiple effect evaporator, and its bricks are increased, and that becomes it has got a calorific value that is used in incineration. There is a boiler. They'll blend either with coal or bagasse and burn it. They'll generate again a power. So whatever ash is generated, that has got a rich in potash, it can be used as a fertilizer. So this is how a sugarcane factory, 15,000 tons, that press mud, it goes as a manure, again back to the agriculture land. Molasses goes into distillery. Again, whatever waste is coming, it is completely reused. This is a circular economy, we can say. So grain distillery, earlier it was only sugarcane, but nowadays they are using corn, bajra, rice, sorghum as a raw material in a grain-based distillery. So this will generate ethanol, fusel oil, and carbon dioxide is generated. Even in regular distillery also, this carbon dioxide is bottled and sold and used in different purposes. And whatever the solids are generated, that is called a DDGS. This is very rich in protein, and it is used as a cattle feed. So completely there is a recycle. So this is a flow diagram, milling, solarification, liquefaction, and saccharification. Then whatever comes, it goes to the fermentation, distillation. These are the different process. So once sugar factory, you can see what is the capacity. Then and what is the CO2 gas is generated? 18,000 metric ton per month. DDGS is generated. Fusel oil is generated. Okay. So this is again flow diagram of sugar factory. And this is very important. You can see whatever spent was is generated, given to multiple effect evaporator, then it is incinerated. In incineration boiler, either generate a power, or directly you can give it for a dryer. And once it contains very good nutrient value, it has rich in potash, it is sold as a fertilizer. So this is completely properly recycled, everything. So distillery process, they are given in different types, and grain based. So effluent generation, how much is there? After expansion, it is 76 KLD of domestic is also coming from toilets and other things that they have proposed a sewage treatment plant and process treated in ATP and recycle in process to achieve ZLD. Whatever effluent is generated after treatment, they put it in CPU, and that water is used as a cooling tower or as a boiler feed. So this is different water consumption in different type of industries. You can say molasses based and grain based. This is a different water consumption. And here 2003-82, whatever is mentioned, actually it is used by the already existing cane juice. In cane juice, water content is there. That is used here. So there is what stress on water demand is less. And also effluent generation. So ZLD plan. So these are the scheme for sugar factory treatment. So 366 meter cube of effluent is put into the spring chamber, equalization tank, neutralization tank, and aeration tank. Then again it goes into secondary system, intermediate tank. Then two-stage RO, permit for reuse. And whatever reject is there, that is given to multiple effect evaporator. It is evaporated. So this is existing ETP photographs, and Pollution Control Board has made it a mandatory that they should have a online continuous monitoring system. Whether it is effluent or emissions, they should have an online continuous monitoring system, and this is be connected to the servers of State Pollution Control Board as well as Central Pollution Control Board, and will be monitoring. And if there is any accidents, directly alerts will come to the industry. So this is again proposed sugar factory for 1100 cubic meter per day. They have gone for equalization tank, UASBR, then MBBR. These are the different treatment sequences. Then this is sugar CPU, that's condensate polishing unit we call, and whatever condensate is generated, again it is treated and reused for the process. And similarly with the distillery. And the proposed STP, they have proposed sewage treatment plant as well. And coming to air pollution, they have proposed for boiler air pollution control equipment is electrostatic precipitators, and they have proposed electrostatic precipitators. And for DJ set, it is only a chimney followed by acoustic measures. And again, the hazardous waste is mentioned here: spent oil, waste residues, and etc. So this is again the OCMS, online continuous monitoring system, which we are regularly monitoring. And I'll go into a little bit. There is a compulsory that you should have a 33% of total plant area as a green belt. There is a must, and they should plant trees. This is a 2,500 numbers of plants per hectare. So green belt. So this is a layout. So I'll just come to. Okay. So before taking up establishment of any industry, they have to conduct a baseline studies of the surrounding area of 10-kilometer radius, and they should see what is the ambient air quality in existing this one, water quality, soil environment, noise level, socio-economic in 10-kilometer radius. And they should also see the predominant wind direction. Where is the maximum wind direction is there? And they calculate what do you call ground level concentration. This is a baseline environmental details, and we'll study once what was earlier prior to the establishment of this industry and what is after establishment of this industry. We'll be regularly monitoring. So these are the values of particulate matter 10, PM 2.5, SO2, NOx, and etc. This is air quality index, a present one. So it is satisfactory. So this is a GLC, ground level concentration plume. This is put in some software where we'll come to know what will be the maximum ground level concentration at what location. So that is regularly monitored, and this is during depending on predominant wind direction that is assessed. So GLCs of sulfur dioxide, GLCs of nitrous oxide, and all is environmental based baseline environmental details. This is presented before the public, and their opinions are taken. Not only environmental this thing, even the biodiversity in the study area is taken into studied, and we assess whether it will have any impact on this biodiversity. And similarly, that habitats in study area will be taken. What are the plant? What are the crops they are growing, and what is water availability, and etc. So these are the few things I presented. I open for discussion now.
Yes, sir. We have one particular question.
Yes, sir. Yes, sir.
Because these participants, I just wanted to inform, sir, there are more than 200 participants. And these participants are spread across India. So they are from all the places, right from northern India, northeastern India, and southern part of India. So they have the online exam now at 6:30.
Okay.
So, however, there is one particular question that we can take up if you don't mind.
Please.
Rest of the questions I will share you through email, sir. You can.
Fine, sir. Fine.
Sir, there is a question from Vinay. He is asking, what is your opinion on the groundwater pollution happening in major cities? Overcoming surface pollution is fairly easy compared to aquifers.
That is a very serious matter. Actually, nowadays, even we have stopped stormwater facility also recharging pits in industries. Earlier, what was happening? They were just putting effluent was going into the groundwater, and in some cases we have noticed, and we have taken action, and that reclamation is also done. They pump out all the contaminated wastewater, water if any groundwater is contaminated, that is also done. Example, in Bidar, regular monitoring is carried out, and fresh water is injected. So many things are done, but the best is prevention. So instead of doing the post-mortem, the prevention is very important, and we have certain protocols to see that whether this waste or whatever chemical waste is there, it is not injected or does not percolate in the groundwater. That we are taking all, we have got all the protocols for that. Even for distillery or pharma industries, will be regularly monitor surrounding borewells, groundwater, and if there is any contamination, immediately we will take remedial measures, and at the generation point as well as at the end of the pipe. That is how we are doing it. Yes, sir. Yeah.
Yes,
I hope it's okay.
Yes, sir. Yes, sir.
Okay.
Yes, sir. With this, I wholeheartedly thank you, sir, for your valuable time and such a nice presentation on waste management, right from hazardous waste management. You have also touched upon landfills. You have touched upon how the treatment plant works, and with such case studies and realistic photographs, we are overwhelmed, sir. And thank you so much for sparing with your busy schedule.
Thank you.
Time, sir. We hope that such kind of collaboration, such kind of delivering of knowledge will be done in future days also, sir.
Definitely. I'll collaborate with you. Thank you. Sir.
Pleasure, sir. Thank you so much, sir. Have a pleasant day, sir. Thank you.
Thank you. Bye.
The participants can stay here only, for which I will give some information. If you have any doubts related to the examination, you can pose me. I request Basavaraj